we should go with like okay, yeah, this is, you're trying to train. So this, just hit F5.
Yeah.
Is it in Word when you do it? It's just that. You don't put that in there. That's right. Later on.
What time are you going to be done? I'll make sure you get uploaded, okay?
Let's see. It'll be about 10:55. Okay, so when I finish, I go ahead and hit it again.
Well, it'll say you'll have stop and pause with these two options. Exactly.
Okay, that's what you say.
Select your pen up here.
Okay.
Razor. When you get done using it, when they do something on the screen, make your mouse. We should be correct. This is like the first.
Okay, this is for the first one. Good morning.
Good morning.
You guys excited to be here? Yeah, I am too. Okay, I'm Valerie and you, Sam. This is band 568. What I'm going to try to do, and as you know, just like Dr. Ashman, I'm going to try to use the new technology, so we'll see how that works. It's hard for me not to write on the board, so I've got to make myself stand over by the podium and not get outside of the camera, but I think it'll be helpful to you when you come back in December to do the online portion to be able to have access to this. So, what I'm going to do is I'm going to start out, and I know that each of you, I don't want anybody to panic. Some of you are going to be, some of you have been through the undergraduate EMBA program and have had one or two statistics classes. So this is going to be sort of a review. Some of you have a degree in another area and perhaps don't have a statistics class. So this will be, I'm going to cover everything that you need to know so that you're going to bring us all up to the same page. So there's no need for you to panic. Some of you have had a statistics class and don't remember it. Which is, or you claim that you don't remember it. So again, we're going to do a review before we get started so everybody will be comfortable and we'll all be, like I said, on the same page. So what I'm going to do is I have a review for you, and let's see how this works. There you go. We're going to talk about, there's actually two types of statistics. We have descriptive statistics, and in that case what we do is we gather data, and then we just describe the data that we collected. So just like if you are a sports fan, a baseball fan, and you look at the RBI or whatever for a particular baseball player, those are descriptive statistics, right? They describe the performance of that particular baseball player over his career. All right. I thought that would show up there, but obviously that's not working. Let's see. All right. Sorry. All right, the next type of statistic, I thought it was going to show on
That's right. And you got to turn the thing to you.
You guys are so smart. Do you think that's the, doesn't it look like the remote control for the digital projector? No. This is so sad. I'm the only type of remote control I've seen for the, does this look like? I hate to press any buttons, right?
Press the power button.
Yeah, this, does it look like? Well, I'm afraid it's for this, because this says NEC. I don't know if that's the same. You think this is it?
Yeah, that one's all turned on, I think, yeah.
It's on.
I think you just turn the TV
I know. It's fun, you guys.
Maybe it's another
I'm
remote.
so excited. Yeah, I remember. This is Dell. Is that
Yeah, that's the... Yeah,
Yeah, these are down.
Okay, we'll try it. I'll be turning on stuff we need. This doesn't look anything like the remote control we have in the other classrooms. There's a whole bunch of buttons in here. None of which say power. All right. I'll tell you what I'm going to do. I'm going to go get Dr. Ashline. Maybe I should just call him. I apologize, you guys. I'd like for you to be able to see it.
say it's good.
Did you just sit in the class or just in the line? See, these don't look like the digital projector thing we see.
They are though.
Oh, there you go. He makes it look so easy, doesn't he?
There it is.
Was it, is it going to come out here?
It takes a few minutes.
Just line up.
I don't have to do anything to make it come up here.
What? No, it's coming. See it. See the screen? Yep. Yeah.
Like it, but it doesn't come on that thing?
No.
Okay. That thing goes all the time?
You don't want it to?
I don't care, don't
It's
worry.
distracting. It's distracting. It's distracting. No, y'all sit there and watch it. You're
Thank you. Man, my spark was going down. Okay, sorry. What?
No, thank you.
Oh, thank you very much. Appreciate it. More than you can. Should have heard him laughing hysterically when I'm screaming, Leroy, come. Okay, everybody did not expecting that. All right, we talked about descriptive statistics. If you haven't figured out, I'm a little technically impaired when it comes to anything with the computer. I mean, I could do statistical analysis, but I have a hard time printing, without having problems. So anyway, yeah, I don't know what it is that computer that it freaks out or something. All right, so descriptive statistics, we take data and then we just describe the data that we've collected. Inferential statistics, on the other hand, is where we take data, we take a sample, right, of data, and we use that data to make inference about the population as a whole. All right, everybody understand the difference between the two? In one case, we just take data and describe the data that we have. In the other case, we take a sample of data and we use that data to make inference about the population as a whole. In other words, the entire group, right? It's just like this. How do they decide what we watch on television? What shows are going to be on?
Nielsen.
Right, we have surveys, don't we? We're trying to access the viewing public. It's impossible to to find out the entire viewing public and what they'd like to watch. So what do? They have a sample of households, and based on what those households watch, what the proportion that watch a particular show, that determines what the rest of us get to see on TV. All right, that's inferential statistics. It's where you're taking a smaller group and making an inference about the entire population. What am I doing here? All right, here's the basic terminology. We're going to talk about what I think is the most important four definitions, right? The population. The population includes all the elements of interest. What does that mean?
It's the whole group.
That's everything, whatever it is. And who determines what the population is? Whoever's doing the study, right? In other words, that you could, let's say that I'm interested to see whether or not, because of the economy, more non-traditional students are returning to school. What is my population? Students. Which one? College students. Okay. Am I interested only in Texas or in the United States or the world? Well, it depends, right? I would have to decide what the population is. Are we talking about public schools, private schools, or all schools? Okay, so you determine the population. Whatever that is, the population includes all the elements of interest. All right, the sample, and what is the sample? The sample is simply a subset of the population. All right, so, and typically we refer to a random sample, right? And what is a random sample? That means every element in the population has an opportunity to be selected when you take the sample, right? All right, so the sample is going to be just some subset of the population. Now, this is important to remember to understand statistics. Every time you take a sample, right, let's say, for instance, let's say the entire, let's say the fall semester had started, so all the students are here. We have about approximately 16,000 students. I ask each of you to go out and take a sample of 30. Okay, let's say that we're going to determine whether or not the average age of college students has risen because more non-traditional students have returned to school. So I ask you to take a sample of 30 students, each of you, and determine the average for that particular sample. Now, are those samples going to be the same for each of us? No, they're not. So that's important to write. Depending on the sample that you select, you're completely dependent upon that. All right, the sample that you select. In some cases, you might get a sample that's representative of the population. In other cases, you might not. And that's the thing about statistics. We're really guessing, right? Based on our sample, we hope this is a good guess, right? And that's what we actually do in statistics is we're guessing because we're not using part of the whole. The parameter is a characteristic of the population, right? The parameter is what we want to know. That would be the average age of all college students. Maybe in the United States, maybe in Texas, it depends on which particular population you're interested in. But the parameter is the true value, what we're looking for, what we want to know. Now, why can't we just calculate parameters? Why can't we just get the characteristics of a population? Let's go back to the viewing public. If you have a new show that you're producing and you want to know whether or not all of the viewing public or a certain percentage of the viewing public watches your show, how do you determine that? Yeah, but if I want to know the parameter, that's a characteristic of the population. How would I be able to measure the entire viewing public? I wouldn't, would I? I couldn't do that. It's impossible. All right, so it's impossible. You think about it. In most cases, it might be possible if you have what they call a finite population, right? It's one that's small enough that you could actually measure. Even that, sometimes it's impossible to do because we can't. People are not accessible, right? It might not be possible for you to get a hold of them. I always like to give the example. Sometimes we don't want to measure the entire population. Let's say that we produce light bulbs. That's an example that I've used in my undergraduate classes. The students like this. All right, we used to talk about the tensile strength of wire, but let's say we're producing light bulbs, right? And when we get ready to sell our light bulbs, we find out that we have to know the average lumen hours. They have to be on the packaging before we can sell these light bulbs, right? There's some rule about some consumer law about that, right? So we need to know the average lumen hours of our light bulbs. What do? Yeah, we start burning them, don't we? And we test, to get the value of the parameter, we'd have to burn them all, wouldn't we? And then when we finish, for every time what we do is we start the clock and we turn on the light, however we hook up the light bulbs, and they start burning, and as soon as one went out, we'd record the time, and as we go along, we continue to record the time. When we finish, we take the average, and we would know the average lumen hours of all of our light bulbs. So what's the problem? We burn them out. Okay, so in some cases, finding the value of the parameter is destructive. In most cases, it's just hard to get. All right, it's hard to measure in terms of the viewing public and lots of things like that. It's really impossible to get. All right, so what we want to know is the parameter. Guess what? We're going to settle for what we call a statistic, right? And the statistic is the corresponding characteristic for our sample. In other words, if I want to know what proportion of people who watch some particular show, or I want to know the proportion of students that are non-traditional, right? Instead of being able to find out the parameter, I can take a sample and calculate the statistic. That statistic is my best estimate for the value of the parameter. Now, let's go back to what I was talking about earlier. When I take a sample, you take a sample, he takes a sample. We all have different samples, so we also all have different statistics, don't we? If I ask you to find the average age of students from your sample of 30, are our statistics, our sample means, are they all going to be the same? No. We took different samples. Would they have the same mean? No. They wouldn't have the same average, would they? A statistic is a random variable. What is it dependent upon? It's dependent upon the sample that you have collected. All right? So our statistic is an estimate for the parameter, but our statistic is a random variable and varies in value, right, by definition. It varies in value depending on the sample that we select. So you can see the problem. What we want to know is the parameter. It is a fixed value for some period of time or area of space, right? In terms of the average age of students, we could say today or for the fall semester, right? In a particular point in space. But To estimate that, we would take a sample, and again, we could get many different values for the average age based on our sample. All right? Okay. All right, again, we will use the information from the sample to describe and make inference about populations as a whole. All right, we're going to use statistics to estimate and make decisions about parameters. All right, what we're interested in is not so much descriptive statistics because that's fairly straightforward. If you have a computer package and you put in the data, you can just press a button and do every descriptive statistic known to man. Right? You print it out, and then if you, assuming you can understand it, you can spout those statistics. In terms of making statistical inference, what we would use it for in business is to estimate things like estimate demand and so forth, or if you want to test a hypothesis, right? So two different kinds of statistical inference. We typically are interested in estimating the value of the parameter. What we do is we use the point estimate, and then which is our corresponding statistic, and then we'll come up with an interval around that estimate. And then to test the value of a parameter, we're going to, again, we'll make a hypothesis or make hypotheses, and then we test to see what we believe to be true. Now, the most important thing to remember is this is based on probability. We're taking information from part of the population and trying to make inference about the population as a whole. We are always guessing. Now, we use mathematical, we base it on probability, and so that we know ahead of time what the probability that we're right or the probability that we're wrong. Unfortunately, after the fact, we don't know. We either are right or we're wrong, and we don't know whether we are right or wrong. Okay, so we're guessing. Okay, again, the value of the parameter is what we want to know. We're going to settle for the value of the statistic and hope it's close. Kind of sad, right? Hope it's close, but that's what statistics is about. We use statistics and a lot of other quantitative techniques, to make decisions when we have uncertainty. I mean, it's like the other day, I went to Dairy Queen, pulled up to the thing, I had my grandchildren with me, they wanted ice cream. Guess what? I don't have any ice cream. That's the first thing they said to me. Welcome to Dairy Queen, we don't have any ice cream. You're like, I'm sorry, but am I at Dairy Queen? Because this is where you get ice cream. And my grandkids are screaming in the back seat. What do you mean you want ice cream? What's wrong with that? I mean, how do you run out of ice cream? You don't predict demand very well, do you? Or something. Maybe you have a mechanical rumble or something that goes with the ice cream. But, right, it's like if you ever go someplace and you want something and they're out of it, right, it's because they didn't do a good job of predicting they had demand that was higher than they thought or whatever. So again, how do we come up with those numbers? We use statistics, quantitative techniques, right, based on past performance typically or something like that, and we make decisions, all right? So again, what we do is we're going to settle for our statistic. We hope it's close. We're not ever assured of that, but again, we use probability to do our best here. All right, we're going to use Greek letters to denote parameters, right, just to make it, if you notice up there, we have mu, the first notation up there is mu, which is the population mean. That's supposed to be pi. I know these look different depending on the font that you use, right? The second one, of course, is pi. That's the population proportion. Sigma, these are Greek script letters, right? Except for the last one, which is actually, well, it's a block, right? Sigma, and then the last one is beta. We use Greek letters to represent the parameters, and we're going to use Latin letters to represent our statistics. All right? So X bar, we'll go back over these. X bar is our best guess for the value of mu. P, which is the sample proportion, our best estimate for the value of the population proportion. S, which is the standard deviation, is the best guess for sigma, the population standard deviation. And B is our best estimate for beta, which typically represents the slope. All right. And this is just an example. We're going to go back through. You don't have to have those memorized now. All right? All right. All right. Now, the most important thing before we get started in doing any sort of study is we're going to talk about the different types of data. Of course, we have both quantitative data and qualitative data, right? In business, a lot of times what we're interested in is qualitative data, which kind of is tough because qualitative data is obviously the structure of the data is such that really all we can do is count or calculate proportions or percentage. In other words, let's say that you, say you're interested in, what is that, hardy plank? Say you're going to sell hardy plank to put on houses, okay? Now, you want to know whether or not someone might be interested in it, maybe, or someone might be able to use that sort. I could use it on my house, I think. I have a wood house, right? All right, so if you're interested in the proportion of people or the number of people in a particular area that might be able to use hardy plank on their home, right? What are you going to do? How do you get that data? Well, you start calling people, or somehow you're going to survey, right? And when I ask you, would you be interested or could you use hardy plank on your home, your answer is going to be what? Yes or no, right? That's qualitative data, isn't it? Or do you like this particular product or do you not like it? Again, that's qualitative data. Or I have 3 products, which do you prefer? That's qualitative data. That's different from quantitative, right? Quantitative is when we have a real numeric measure, like what? How much did you make last year? That's a numeric measure, right? How old are you? Your age is a numeric measure, right? That's quantitative data. Those are numbers, and not to be confused. We have some numbers that are not quantitative measures. Do you agree? Like your telephone number is not a quantitative measure. Your social security number, your employee ID number. What else?
Like hair color.
Yeah, okay, now the hair color would be what? That's qualitative data, right? All right, so we determine ahead of time what kind of data we have, and then we are dependent upon the data that we have to use a particular statistical technique. In other words, in some cases you have to have quantitative data. If you have to have quantitative data and you don't have it, you can't use that technique. Everybody understand, right? So our techniques are based on what kind of data we have. All right, we're going to talk about, and probably most of you, the first time you saw this, I think the first time we talk about scales of data measurement, do you remember the first time you were exposed to that? It wasn't in a math class. I don't think the first time I heard it. It actually, we were talking about, it wasn't, I don't remember exactly what it was. It was in a science class we were talking about data, right? All right, so we have 4 types of data. Nominal and ordinal data are what? Qualitative or quantitative? Qualitative, right? Qualitative data. How the scales of data measurement go from the least amount of structure to the most amount of structure in terms of the data, all right? So we start with nominal data. What does nominal mean? In name only, okay? And that's like hair color, right? If I said hair color, what do we have? We could be blonde, we could be brunette, we could be redheads, we could have dark brown hair, whatever. All this. Of course, today we have all different colors of hair, right? Because you can buy them in a box and have every possible color that you can have, all right? But that's nominal data, right? It's qualitative data that has no order to it. Do you agree? What about male and female? That's nominal data, isn't it? Qualitative data that has no order. What's another example of nominal data? I mean, there's millions of them, right? The color of your car, your political affiliation, that's nominal data. There's no order to it, right? It's something that you can categorize, but that's it. There's no, you can't do any ranking with it. But that's the lowest form of data. The lowest form of data is nominal data, qualitative data that has no order. All right? And lots of things that now a lot of times in business we're going to have qualitative data, but we're going to have what we call ordinal data. And ordinal data is qualitative data that has a natural order. Like, if we're talking about your preference for a product, you can rank them, can't you? First, you like this one the best, you like that one second best, and that one third, right? A lot of times we use what we call a Likert scale, and Likert scale is ordinal data, and what that is like a state your level of agreement with the following statement. Have you ever filled out a questionnaire like that? State your level of agreement with the following statement. So they give you a statement, they'll say, strongly agree to strongly disagree. That's qualitative data that is ordinal. All right, there's a natural order to it. What else would be ordinal data? say if you have, like when you have shoe sizes when you buy flip-flops, right? They have small, medium, large, extra large. That's ordinal data. Military rank is ordinal data. Categorizing a used appliance as in poor condition, good condition, excellent condition, right? That would be ordinal data. All right, everybody understand? Now, these are both qualitative. These scales of data measurement are both for qualitative data. All right, again, nominal is qualitative data that has no natural order. Ordinal data is qualitative data that has a natural order. All right, now, we're moving again along in terms of structure for the data. Nominal data has the least amount, then we have ordinal data. There are more techniques we use, typically non-parametric techniques that we use for data that is ordinal. We have ranking techniques that we can use for that. Again, but once we get down to interval and ratio data, which are the last two are quantitative classifications for quantitative data. Interval data is quantitative data that has no natural starting point or zero level. I remember the first time I taught a statistics class, I actually was teaching the first undergraduate class. And my first lecture on types of data, I looked through about 5 books, and the only example that they gave for interval data was Fahrenheit temperature. So I come to class the first time, I said, okay, an interval data, that's quantitative data that has no natural zero level, like Fahrenheit temperature. Somebody in the back raised their hand. Could you give us another example of that? I was like, no, I don't have an example. But since then, I have come up with a couple of others. Your GMAT score, would that not be interval data? Because it doesn't have a natural starting point. Actually, you know what I'm saying, in terms of the measurement, and I'm not sure what you would say the GMAT say. Let's talk about an IQ score. That would be a good example, right? An IQ score measures your intelligence, right? It's actually a ratio of your mental age to your chronological age, right? So an IQ score, there's no natural starting point there. In other words, there's no measure for an IQ that shows the absence of temperature. The absence of intelligence, right? That doesn't make sense, right? Do you agree? It's the same thing when you think about Fahrenheit temperature. 0 degrees Fahrenheit is not the absence or the starting point for temperature. Do you agree? So the problem with that sort of data is that the ratios don't have meaning. In other words, 50 degrees is not twice as warm as 25 degrees. 100 degrees is not twice as warm as 50 degrees, right? When we're talking about temperature. So in terms of that type of data, it is quantitative data, yes, but the ratios don't have meaning there. All right? Now, the last type of data, of course, the type of data that has the most amount of structure is ratio data. Almost all quantitative data falls in the category of ratio data. It is quantitative data that has a natural starting point. Your height, your weight, the rate of return, your income, the selling price of a product, all of those types of that type of data is ratio data, right? It's quantitative data that has a natural starting point. And typically we're not going to differentiate between interval and ratio data. All we care about is it quantitative, then all of the techniques that we talk about in here, is it required? Of course, you can use all techniques, but in terms of descriptive statistics, when you have ratio data, you can calculate anything, right? Again, that's the highest form in terms of structure, in terms of types of data. But ratio data is the one that has the most amount of structure. All right. Now, if I was going to teach it, one time I taught in a class that was, it was the gifted and talented class for one of the elementary schools, 3rd through the 5th grade, right? They asked me to come in and talk about statistics. I was like, really? You're going to talk about these kids, 3rd through 5th grade? What do you think we talk about? If we're going to talk about statistics, measures of central tendency, right? What are the measures of central tendency? Like the mean, right? The measure of central, or all the measures of central tendencies are attempts to find what they consider to be typical values, right? What is the average value of, or the average age of students enrolled at Sam Houston State University, right? If I was interested in whether or not that was increasing in value, All right, I'm interested in that. The average is a measure of central tendency. Now, there's lots of different measures of central tendency. We talk about the mean, right, which is probably the most. We use the mean the most frequently because it has great mathematical properties. Okay, so we like the mean, which is what most people refer to as an average, right? And there's more than one type of mean, but we're going to talk about just the arithmetic mean. Okay, and in this case, if you want to calculate a mean, it's got y bar there. I don't want you guys to get hung up. I typically use the variable x. When you get into multivariate statistics, we usually use y. It doesn't matter what you call the variable. If we're calculating values, if we're looking at differences, we would call that variable d, and we would calculate d bar. In this case, we're going to calculate y bar. Y just happens to be the name of the letter that we're using to represent the variable. Sometimes we use x. But x bar is a symbol for the sample mean. And how do we calculate a sample mean? The sum of the observations divided by the number of observations. So just to review, the sigma, the block letter sigma up there on the numerator there, that means to sum, right? You remember that? So we're talking about sum all the y's up. In the denominator, we have lowercase n, which represents the size of the sample. So if I took a sample of 30, we would add up all the values. If we're talking about ages, I took a sample of 30 people. I got their ages, I recorded their ages. I would add all 30 ages up, divide by 30, right? And that would give me the mean age for the sample of 30. All right? Okay, now, again, the most commonly used measure is the mean. We have other measures of central tendency. We use the median. What you need to be careful about is this. We use the mean most frequently when we make statistical inference, again, because of its mathematical properties. But there are times when the mean is not appropriate. All right, there's some problems with the mean. Does anybody have any idea what one of the problems might be?
Standard deviation. The mean can be really high.
If there's a lot of variability?
Right.
That's true. What else? Number one, what we just talked about. What did we talk about? Type of data. What if we didn't have quantitative data? Could we calculate a mean? No. All right, with qualitative data, you can't add. Right. Well, let's think about it for just a second. Let's go back. That's what we were talking about. Here's the scale of data measurement, right? We have to determine ahead of time in terms of what technique or what statistic we need to calculate, what kind of data we have. Nominal data, can you add up hair color? Can you say how many people have at least red hair? Can you do that? No. Right? Because there's no order to it. So no, we can't do that. Okay, ordinal data. Now when you get down to ordinal data, you can do what? You can order it. That's a good thing, right? So if you were, let's say we were asking students, we were trying to find out the average classification for students in some particular class. So we rated, instead of using hours completed, we're going to use classification. So freshman, sophomore, we're talking about undergraduate students. Freshman, sophomore, junior, senior. So what do we do in that case? You want to know where the middle is. We put all the freshmen first, right? And then the sophomores, and then the juniors, and then the seniors. And if we included graduate students, they would be last, right? And then you just find the center of the data. What is that? That's not the mean, but what is it? It's the median. The median is the value in the center of the data. So if we have ordinal data, we can find the median of that data, right? But we can't calculate a mean, can we? We can't find the average when we're talking about classification in school because that's not quantitative data. All right? And again, as you move down interval ratio data, then you can calculate a mean, as long as it's quantitative. Right? We could find the average temperature in 15 cities across the country, couldn't we? And that's interval data. All right? As we move down again, first we have a name order only, then we have order, so we can actually order the data. Well, and a good way to look at this is think about ordinal data as this, the place, finish, and a race. Let's say the three of you ran a race. All right? You came in first place, you came in second place, you came in third place. All right? You ran the race in 1 minute. You ran the race in 2 minutes. How fast did he run the race?
3, between 1 and 2.
That's exactly right. It's between, right? 1. I said he was second place. He was second place, right? 1, 2, and 3. So 1 minute, 2 minutes, how fast did he run it? We don't know. We just know what? Between 1 minute and 2 minutes. Okay? So that's ordinal data, is it not? First place, second place, third place. We can order it, but it's not quantitative, is it? Think, I don't know, first place, second place, third place. That seems quantitative. No, it's not quantitative data. Right? That is ordinal data. It's all we can do is rank it. We can't say we don't know how fast he ran it because we don't have that number. All we have is first place, second place, third place. Now, we move into interval data. That's where the word interval comes from. When we have equal intervals between the data points, which we didn't have here, we don't know whether we did, right? First place in terms of time. Equal intervals between, then what happens? All of a sudden we can add, we can subtract, right? We have equal intervals between. Now we have quantitative data. All right. So, is that a little bit more clear now? When we start to calculate a mean, we have to have either interval or ratio data. So, when do we use other measures of central tendency? When we don't, well, number one, when we don't have quantitative data. All right? I think the three most common measures of central tendency would be the mean, the median, which is, and I'm talking about the arithmetic mean, the median, which is just the center data, the center point in your data set, right? Or between the two middle ones, right? That's what we would call the positional average, right? The median is the positional average. It's the one that is located in the center if you rank your data from smallest to largest or largest to smallest. All right, and then the last one is the mode. Does anybody remember what the mode is? That's right, the one that occurs with the greatest frequency, right? Do we care about that? Maybe, that's right. What if we have a sandwich shop and we sell 5 different types of sandwiches? Do we care which one is in terms of purchase, the one that's most popular? Do we care the one that is sold the most frequently? Yeah, we probably do. Why? Because that's right. Because if it's BLT, we need to make sure we have enough BL and T, right? Right? We don't want to make sure. So that's important. What about if you sell shoes? Do you want to know the modal shoe size in terms of sales? Yeah. Because you might live someplace where people have really small feet or really large feet or whatever it is. The people that come in your store, you want to make sure you have shoe sizes that fit those people. So you want to be able to predict demand. So in that case, the mode would be used, right? All right. Okay, again, the most commonly used measure of central tendency is the mean. We're going to use the mean for statistical inference. Now, let's talk about the mean for just a minute. It's what you call the gravitational center of the data set. That's reading. It's got really great mathematical properties, right? I'm excited, okay? All right, let's talk about that. Let's just say, since we were talking about age earlier, let's talk about age. So if I have, let's just say that my arm is like a number line. Okay, we're going to do like a teeter totter, right? Okay, my arm is a number line, and I give each of you an equal weight, because this is an arithmetic mean. So with an arithmetic mean, as opposed to a weighted mean, in an arithmetic mean, every element gets the same weight, right? Because we're going to add them all up and just divide by the number so they all have the same weight. So I give each of you a weight, and on my arm we're going to put, the ages here. We start with about, I don't know how young the youngest person in here is. Yeah, I'm sure it's say 20 something. And then we have 25 and 30, and if we have anybody older than that, I don't know. Okay, so anyway, so each of you come up, and they'd have the marks on there, and you put your weight where your age is, right? And at the end, when everybody gets all their weights up there, and if you had the same age as somebody else, you can stack it on top, right? The point at which it balances is the arithmetic mean. Okay, the point at which it balances is the arithmetic mean. Okay? Now, what we were talking about is when do we not want to use the mean? What happens if I have a weight to, or what am I going to do? I'm going to put my weight way out here someplace. What happens when you way out here? Pulls the mean, doesn't it? It's going to pull the mean toward it. Always, when you have extreme values, whether they're a lot smaller or a lot larger, it's going to pull the mean toward it, is it not? Sure. Now, depending, we have 17 students in here, so I only have 1/18 of the weight. when we talk about smaller group, if we're talking about 5 people, then I have 1/5 of the weight. I have more influence on the meeting, right? But as we have larger samples, then I would have less influence. But yes, and I always think of the example, and I think I can remember this, but this is an old example, but back when, what school was it? I think it's North Carolina. The geography department at the University of North Carolina had some advertisement that they had the average salary of their graduates within the last so many years was something like $220,000 a year. Yeah. I was like, really? I thought geography sucks. Anybody can make any money doing it, right? I mean, maybe, I guess in the oil field they need people that are, but I was just thinking that's probably unlikely. I would have gotten a degree in geography myself, but what's the problem with that? They have somebody who graduated from the University of North Carolina, and I made it. Who is it? Is it Michael Jordan? Is that right? Did he go to the University of North Carolina? Yeah. And he majored in geography. Well, he's not practicing geography, right? He was playing basketball at the time, but yeah, so they advertise that. So that's misleading, right? I'm thinking most of those poor souls were making very little money, and he was making a whole bunch of money. But when you average them, on the average, they make good money. Right, so that's misleading. So whenever you're talking about census data, and later on we're going to be using census data, I like to use census data whenever you have to calculate something because it's something everybody can go out and find, and you can pick your own data set and calculate stuff, and it's a neat place to find out too. A lot of times we're interested in census data for marketing and things like that. Okay, but in the census data, when they talk about income, do they use the mean? What do you think, Brian? Do they use the mean? No. Why? Because there are people who make a lot of money. Now, there's sort of a lower end to making money, right? Like making no money, that's the lower end of that, right? But is there an upper limit to income? I don't know, but I'd like to find out. Just for fun, just a couple of years, I'd like to have all no limit, just keep making it. No, there's not, right? So what happens is people who make a lot of money obviously affect the mean significantly, right? So they're pulling the mean income would be very high if you have people that within that population that make a lot of money, right? It makes the rest of us look like we're doing real well. When in fact, we might not be doing so well, but we have 1 or 2 people out there making a whole bunch of money. It pulls the mean toward it, right, in terms of average income. So whenever you look at most of the income numbers that you look at for the federal government or the state, actually, it's going to be based on the median income. Why is that? The median is not affected by extreme values, right? It's just the one in the center. All right, so in some cases, the median is the best. All right, but again, for our purposes, we're going to use the mean because it's got those great mathematical properties. Now, let's talk about dispersion or variability. Are you having a great time? Always, right, always. Okay, let's talk about measures of dispersion. Now, if I told you that all we really need to know is a typical value, what would you think? This is going to be an easy class, right? That's all we need to know are typical values. You know how to calculate a mean. Unfortunately, that's not true. I didn't know that. Right? Well, you're here even. I get to torture you for 6 days. So obviously there's more stuff to this than just the measure of central tendency. Although some people, it seems like that's all they're interested in. If I look at the mean. Now let's look here, we have the mean. And the mean is this. Is that all you need to know? No. In fact, I would argue that statistics is more about variability than it is about the center of the distribution. Absolutely. We're much more interested in variability than we are in the average. For instance, you could have a portfolio of stocks, and you could talk about return, okay? And we could all let's say everybody in the room had a return in the last month, or let's say in the last year we had a return of 4.2%. We all had the same return, average return. Now, I might have all stocks that had exactly 4.2%. So I get an average of 4.2. And you might have had stocks that vary around 4.2 by not very much. And you have an average of 4.2. And Paul, you could have one really great stock and a whole bunch of crummy ones, right? And it still averaged to 4.2. So you see what I'm saying? You can have an average. All of us could have the same average, right? In terms of our return on our stock, but our fluctuations in the different stocks could be they could be all over the place, right? Or they could all be pretty consistent. Are you interested in knowing that? The variability of those values as opposed to just what is the average? I hope so. I hope you're very interested in that because that's where all the information really lies, isn't it? And how the values vary around that typical value. I like to tell this story. This is the way that I learned about variability. Let's say that this afternoon when you get through at 6 o'clock, instead of studying, we're going to go on a field trip. You want to come?
Yes.
Yes, then you need to get out. Well, hey, next week I'll ask you again, right? You have not suffered yet. This is only the second day. Yeah, next week sometime. No, people look completely different too by the time we get to the second week, right? The girls don't even mess with their hair anymore. They're like, yeah, they have it up in a ponytail. I keep mine in a ponytail most of the time anyway, but yeah, it's a whole different thing. But let's just say I could take you someplace. So I have a friend who has some property out here. All right, and there's a lake on it. Now, let's just pretend for just a minute that none of us swim. Where we're going is on the other side of this lake. And there's not any way to get to it by driving. We're going to have to go across the lake. We don't have a boat. But that's okay. Because my friend said the average depth of the lake is 4 feet. We just walked across it. I mean, I'm short and 4 feet here, right? There's nobody who's pretty close to the same height, right? We'll be okay, right? We just walk across it. The average depth is 4 feet. Anybody going to go with me?
Go first.
Okay, good. I'll follow you, Dr. B, saying you just walk across and I'll just be right behind you. That's the only way I would go across that lake. What about you? I'm going to go behind somebody else. Why is that? Well, the average depth of the lake is 4 feet. It could be 4 feet all the way across, couldn't it? Well, it might not be. That's right. And the problem is, if we can't swim, and it fluctuates by more than a certain, depending on how tall you are, you'll be drowning, right? So that's important to know. The variability is very important. Okay, so we're going to talk about measures of variability or dispersion. They use different terms. Measures of data variation, measures of spread. Okay, now, before we go on, what did I tell you? What kind of data do you have to calculate a mean? Quantitative, right? All right. Now, to measure any type of variability, any particular statistic where we're talking about variability or spread, it also, you have to have quantitative data to do that. Okay? All right. I picked up the wrong thing. That would be really bad if I turned something off here. All right. Measures of dispersion attempt to describe the spread in the data, right? The most commonly used measure of dispersion is called what? The standard deviation. Do you remember that? I know you're excited about that standard deviation, right? Do you remember what it was? Now, there's lots of measures of spread. What is the easiest measure of spread? The easiest one to calculate. Think about this. If I told you, go out and take a sample of 100 people and ask them what their average salary was last year. Do you think anybody give you that information? Maybe. But say you got 100 observations. What's the easiest thing to tell me about that? You wouldn't even have to do anything. Actually, if you enter it in the computer would what? What's the first thing you do with the data set? You'd order it, wouldn't you? And what can you find if you order a data set? If you order a data set, what can you find out about it? You can find out the
Median.
I'm talking about but just ordering it. What can you tell by just ordering the data set from smallest to largest? Well, you know the smallest and you know the largest, right? Now, the difference between the largest and the smallest, and then what is that called? It's the range. The range of your data. That's the easiest thing. Now, I was an accounting student, undergraduate accounting student. What I know is this. If it's easy to calculate, we're never going to use it. Do you think that's true? Have you ever done any taxation? I was in tax. If it's easy, do we use it? No. We only take the most complicated method. There's 2 different ways to do it. Well, they'll teach you the easy way, and then they say, we never do it that way. Straight line depreciation. Do you think they've used that? Not ever. Right? All right, so, and then they may use straight lines sometimes. We obviously do, but typically they don't. Okay, so that's something. Now, what is it? Why is the range? Why do we use the range? It's easy. Too early in the morning for statistics, really, isn't it? And I don't know who I made mad by having an 8 o'clock class and teaching Tuesday, Thursday, Saturday. It's with that. Why doesn't he get a regular faculty member? I have a real job. I have to work Monday through Friday, but still I have to come in on the phone. At 8 o'clock, how did we get off on that? What were we asking about? Let's see.
Range.
The range.
The range.
Because the range has 2 amounts that could possibly be at the opposite ends of the spectrum that could be far outside the normal.
The rest of the day?
Far away from the median.
Absolutely. Did everybody understand what he said? It's like this. The range is the difference between the largest value and the smallest value, right? Now, if the range is small, it gives us a lot of information, doesn't it? Right? If there's not much distance between the largest value and the smallest value, then we know a lot about the data set, right? So if the range is small, it tells us a lot. If the range is large, what does it tell us? Nothing. That's what his point was, right? That's the point he was trying to make. It doesn't matter how far apart those are. We're only using 2 of the values. Those values could be a long ways from most of the data, right? The largest one could be a long ways from the center of the data. The smallest one a long way. All it tells us is what? The 2 extreme values, they're a long ways from each other. But it doesn't tell us anything about the rest of the data, does it? That's the reason we don't use the range. It uses only 2 values, right? So what do we want to do? What we really are interested in is what? How on average do the data points vary around what? The typical value, which is the mean, right? Isn't that really what we want to know? On the average, how do the data points vary? For the depth of the river, I'm very interested in that. How do they vary around 4 feet? There's not going to be much variation. There's just a little bit, right? All right, so all right, now, again, they're using the variable y, right? So we're talking about these are just y1, y2, y3. That's the data I've collected. And we just arbitrarily assign numbers to the data points, right? We're just talking about we take the first data point and the second number. Now, what are we doing? We're subtracting from that the mean. Remember y bar, x bar, d bar, whatever happens to be our variable. That's the mean. How do we calculate it? We added up the data points divided by the number of observations that we had. We got the mean. So what we're doing here is for every data point, we're subtracting the mean from it. What we're trying to figure out is how the values vary from the mean, right? Each of these are called deviations from the mean. In other words, if the mean age of the students in this class is, let's just say it's 26, the mean age is 26, so we take Paul's age minus 26, that's his deviation from the mean. You take my age minus 26, wow. You have more than 26? Less, okay? All right, so what does that mean? That's the deviate. That's how much I'm deviating from the mean. What does it mean to deviate? Deviate. Just to be how you differ, right? Always. Do you not kind of get a bad connotation? Think about something bad when I talk about a deviant. What's a deviant? I've been called a deviant before. What is that?
Not normal.
That's all it means. Is not normal. I don't know about you, but I never wanted to be normal. Well, in some things, maybe. But no, I mean, normally, I don't want to be like everybody else. I'd rather be a deviant. I want to be different from other people, right? I want to be different. So to deviate just means to be different from the norm, right? So these are deviations from the mean. So all we're doing is we're taking each value and we're subtracting the mean from it so we know how it deviates. Now, if the value is larger than the mean, the deviation from the mean is going to be what? 10 minus 7. Positive, right? If the value is less than the mean, the deviation from the mean would be negative. If it's equal to the mean, the deviation would be what? 0, meaning there is no deviation, right, from the mean. All right? So when we get finished, we have some negative numbers, some positive numbers, some zeros probably. What we're interested in is the average deviation from the mean. Isn't that what we want to know? So how would we do that? We find the deviations from the mean, we add them up, and then divide by the sample size. What's wrong with adding them up? What's going to happen? So you get negative numbers and positive numbers, and what happens?
You got square.
Yeah, you have to do something to them because the sum of the deviations from the mean, what do they sum to? The mean is the gravitational center of that data set. It sums to 0. So we couldn't just find the average deviation from the mean, right? Because our numerator, when we sum up those deviations from the mean, they're always going to sum to 0. So it's talking about this in terms of the measure of spread. This is always true. As that value gets bigger, it means that there's more spread to the data. As it's more tightly grouped, those deviations are going to be small. If the data is spread out, the deviations from the mean should be large. Okay, now, an intuitive measure of spread is the sum of the deviations from the mean, right? We would talk about the average of that. And again, there's a problem with that, and the problem is what? It doesn't work. The sum of the deviations from the mean equals 0. Again, part of the great mathematical properties of the mean messes up our measure of spread, right? Again, because it's the gravitational center of that data set, the positive deviations from the mean will offset the negative ones. That's the reason it balances, right? So we get the sum of those deviations from the mean would sum to 0. Now, what did we say? We could square those values, or what else could we do to get rid of the negative values? What's the other thing that we do to get rid of negative numbers? We could take absolute values, right? I know you were just thinking about absolute values this morning, I bet. Now, in terms of absolute values, what does that mean? We just look at the distance from 0. We don't worry about whether it's positive or negative, right? Because really what we're interested in is how they're deviating, not whether it's above or below the mean, right? They have a measure of spread that's called the mean absolute deviation. That's an excellent measure of spread. But again, we're looking at absolute values, so they take the absolute deviations from the mean and divide by the sample size, and you get what they call the mean absolute deviation. Best descriptive measure for spread. Unfortunately, we can't use it for statistical inference because it's an absolute value function, right? And that's not a smooth function. We need a smooth function so that we can calculate probabilities. All right, so we don't use that. We use instead squares, right? So for the deviations from the mean, we're going to try absolute values again in squares. We're going to actually end up using squares. The use of the absolute deviation is intuitively pleasing, right? It has two drawbacks. It's a pain to calculate, number one, and it doesn't have good mathematical properties or statistical properties. The use of squares eliminates these drawbacks, right? So what happens is, this is called the sample variance. It's S squared. And the reason we use the notation that it's squared, because we're going to calculate in the numerator, what you notice is we have the sum, right, sigma for this to sum, each of the deviations from the mean. We're going to square those first, and then we're going to add them up. All right? So what happens is the negative numbers now, when you square a negative number, like 3 squared is 9, negative 3 squared is also 9. All right? So what happens is we get rid of the negative values, so the sum of the deviations from the mean won't sum to 0. We actually have a number in the numerator to divide by. Right? What happens if you have 0 in the numerator? Well, the number's always 0, right? When you calculate a 0 divided by whatever it is 0. Can we have a 0 in the denominator? No. Not right, that's not defined. You can't use a 0 in the denominator. You can have a 0 in the numerator. The problem is our answer will always be 0. That's not a very good measure of spread, and certainly not correct, right? A measure of spread that is 0 suggests what? there is no spread, right? In other words, if I have a data set that is entirely composed of 4s or comprised of 4s, then what is my measure of spread? What is the range if they're all 4s? 4 minus 4, 0, right? My standard deviation would be 0. My variance would be 0. Every measure of spread would be 0 because they're not varying in value. Does that make sense? All right. So as those values again if the data is tightly grouped, you're going to get values that are smaller. The more spread out they are, the larger the value is. All right. So what we do here is we take each of the deviations from the mean. So if I have a sample of size 30, I will have 30 deviations from the mean. Will I not? Yes. For every value in the data set, we're going to subtract the mean. We square those values to get rid of the negative ones, then we add them up. Because we all know the order of operation, yes? Does everybody know the order of operation? You wouldn't admit it if you didn't, right? I always said, this is where my students taught me this a long time ago. Please excuse my dear Aunt Sally. Have you ever heard that? The acronym, right? Please excuse my dear Aunt Sally. It gives you the order of operation, right? P is for what? Parentheses. We do parentheses first. E for exponentiation, right? That would be exponents and squares, right? Square roots. So, and then multiplication and division from left to right, and then addition and subtraction. Last order of operation, right? So that's exponentiation. We're going to subtract because it's in parentheses. We do the parentheses first. Then we square the result because we do exponentiation before summing, which is what sigma means, and then we add them up. All right. Then divide by your denominator, right? You always calculate your numerator first, then your denominator, and divide the values out, right? That is going to be in what? What kind of units is that going to be in? If we were measuring, let's say that we were looking at the spread of income. Each of you wrote down on a piece of paper what you earned last year. Right? We calculated an average, and for each of you, we took your income minus the average income, we got the deviation from the mean, and we squared it, so forth and so on, and we calculated variance. What units is that in? We started in dollars. I assume everybody earns dollars, right? Is it in dollars? We squared those numerators. It's in squared units. It is in squared units. I would like to have dollars squared. I don't know why, but it seems like it would be better than just dollars. But I'm not sure. How do we interpret dollars squared? What about years squared? I don't want that. I have plenty of years. I don't need them to square them. But they're going to be 1. It's okay to square between 0 and 1. So it's in squared units. That's the sample variance. That's the reason we don't use the sample variance. That's the reason we use the standard deviation. Why? Because that's in squared units. It's just like this. I was helping one of my colleagues the other day he was reviewing a paper. And they were doing a regression analysis, and they were, like they do a lot when they look at economic factors, they were taking the natural log of something. In other words, say they were recording, and it was about loans, syndicated loans, and whether or not they were using a Big Four CPA firm or not, the company that was asking for the money. I don't know if I use the right term. Syndicates where you have one person who leads the loan team, and then they say, "I have this loan. Would you like to play with me?" and give them part of the money. Could you give them $100,000? And if I could take $200,000 from you, so you have some big loan and you're spreading it out, right? Okay, and they wanted to. What is it called?
Participation.
Yeah, but I can't remember. In this paper, they call it syndicated loans. I've never heard that term, but it's where you spread the wealth, right? So a whole bunch of people are going to borrow the money or lend the money. All right, but anyway, we were looking at this, and what they did for a lot of the factors when they were talking about risk is they take the natural log of them. And the reason they did that was because the variables were related to each other, and so what you do is they call it transforming the data. But when you finish and you have a regression analysis, and you have a coefficient, I don't know how to interpret it because what? We took the natural log of that stuff. That's a coefficient that goes with the natural log. I don't know how to interpret it. Same thing here. I don't know how to interpret squared units when we're talking about dollars. Do you? No. The variance is $15 squared. And you say, But now if I told you the standard deviation was $3, right? Then you'd know what? Well, it's varying by about $3, right? That gives you a lot more information. So what happens is this is the variance. The square root, the positive square root of the variance is called the standard deviation, and that's what we actually use as our measure of spread. So you see where we went? We were looking for an average deviation. We ended up having to square those deviations to get rid of the zero, right, in terms of the sum. And then once we calculate the sample variance, we take the positive square root of that, and we get back to S, which is the sample standard deviation. Take the square root. Okay. And there you have, and all I did was put the radical over the formula for the variance, right? That's the sample standard deviation. We are now back in the original units of measurement, and we can use that measure of spread in terms of being able to interpret it, right? All right, the sample standard deviation. Somebody said something, how would you interpret the standard deviation? I would interpret it as the positive square root of the sample variance. And what is the sample variance? It's the sum of the square deviations from the mean divided by n minus 1. Now, you're like, whoa, that's an interpretation for you, right? All right, well, there isn't anything. Our goal, again, was to find the average deviation from the mean, but we couldn't do that, right? If you notice the form there of variance, if you didn't, we'll go back to that page, right, without the radical on there. The variance is always of the same form. Any variance is always of the same form. What's in the numerator? It's a sum of squares. Remember that, because when you're by yourself, back where you live, and you're going through a book, and you start talking about sum of squares, you're going to go, oh, I remember talking about sum of squares one day. A variance is always of the form sum of squares divided by degrees of freedom. The denominator is degrees of freedom. And actually, statistically, it's kind of a complicated thing. Do we have anybody in here as an undergraduate degree, like in engineering, where you have a lot more math? No? Always like, that's good to know, because I don't want any engineers in here. They might correct me on my math, right? Anyway, the degrees of freedom is, the simplest way to do it is to say it is this. You would divide, now think about this. What you'd really like to do is just divide by n, right? Because you're trying to find an average, really. That's what your goal is. Why do we have to say n minus 1? Well, if it were n, would the value be, if the denominator was n instead of n minus 1, would the number be larger or would it be smaller? Is 1/2 larger than 1/4 or smaller? Yeah, what happens? As your denominator gets smaller, right, the number gets larger. Do you agree? The number's going to get larger. Well, if we're talking about a measure of spread, do we want that number to be large or do we want it to be small?
What's the sample? So
What do you think our goal is? To have less variability or more variability?
Less.
Sure, we want less. And why is that? Well, because that measure of central tendency, then it actually means something, right? In other words, if I give you a mean, and there's not much variability, that mean is a good measure of to represent this population, right, or this sample. Do you agree? So the less variability, then our descriptive measures are better, right? So we get, in terms of what is the typical value, right? So we like less variability. Not only that, but we're going to do a lot of things, right? We're going to calculate a statistic and then use that to estimate the value of the parameter. The more variability we have, the less, there's more volatility to it. So you end up with a wider dispersion in terms of your estimate. If you come up with an interval estimate, right, it's going to be bigger, right? We prefer more narrow intervals if we're going to be estimating something. In other words, if I said your average, or your final grade in the class is going to be somewhere between 80 and 100, that gives you more information than saying your final grade in the class is going to be somewhere between 0 and 100. Yeah, thanks a bunch. I knew that coming in. All right, but again, we would like to have more narrow intervals. We like less variability. So what happens is, when we use n minus 1 instead, that number gets bigger, doesn't it? It's going to get bigger. All right? We're doing that to be conservative because really what happened is, in the numerator, we used an estimate. What is the estimate that's in our numerator? What is y bar? It's sample mean. We're using a sample mean when we really are interested in what? The population mean. We don't know what the real mean is. We're using the mean from the sample we collected. Why? Because we don't know the population mean. All right? So when we're looking at variability from a data set from a sample, we're having to estimate what the true mean is. So we have an estimate in the numerator. For every estimate in the numerator, we're going to lose 1 degree of freedom in the denominator. So we have to divide by n minus 1. All right, again, the variance is always of the same form. Sum of squares divided by degrees of freedom. All right, sum of squares divided by degrees of freedom. All right, the sample standard deviation is the constant square root of the sample variance. If it's small, it means the data is tightly grouped. If the standard deviation is large, it means the data is spread out. There you go, sum of squares divided by degrees of freedom down here, right? We use the notation SS for sum of squares, DF for degrees of freedom, and the DF is typically lowercase. Go. In this case, degrees of freedom will be the total number of observations minus the number of parameters that are estimated in the sum of squares, right? We're estimating the population mean using the sample mean. All right. Let's take a little break. Is that good for you? You want to take a break for a few minutes, about halfway through? It's about 5 minutes when you come back. I just thought you'd want to take a break for just a minute to get a little. Just whatever you say, know that it will be picked up off the mic.
Where'd your partner timetable? She's a
teacher?
Yeah.
She's not teaching here anymore. She, and I don't know, I think she might be teaching at, she might be a loan shark. She was selling real estate as well. She didn't, she was and I think she started and then she swapped the file.
Yeah,
Anyway.
I knew she was busy. I just knew her all.
Yeah.
So it's good.
So she's not teaching.
Yeah, I got laid off. I was telling you. I got laid off. It sucks.
Lots of people, a lot of my students are parents.
You ever use this in your job?
No. No, I don't. I'm wondering when I'm going to be using this. I guess you won't. I guess you can. I mean, I'm sure. I'm trying to think. I'm sure there's something you may want to pull or something. Maybe you're analyzing like a pool of investments. You some statistical analysis to see if it's a good investment or not. I don't know. What I always remember from that, I graduated 2 years ago, so it was probably like 3 years ago. what I remembered was it was like just we always use like data from like hair color, size, stuff like that. So you probably. I'm sure you could be creative. I'm sure there's got to be a more practical use to banking for this. I just haven't determined what it is, right? Unless you're analyzing it.
Y'all do participation, right?
Yeah.
Okay, I was gonna say, I didn't think that was just a term I used.
No, you can use syndicate too. I mean, it's just selling a loan. And like, syndicate typically means a pool of loans, but I think you can use the same terminology for it.
She said syndicate is the same thing as participation. I've never heard that term.
We buy participation from AMG Bank or somewhere else. They come up and they call it syndicate.
Are those your best performing assets?
No, it doesn't work.
Really?
Yeah. I mean, once you're in it, you can't get out. We can't sell it like it's loan anymore.
Yeah. It's
They basically say tough shit. No.
So
One's limited recourse and it's starting to get a little bit better. The other one's substandard non-accrual. So it's a big credit to me.
Amagis and Lead Bank.
Yeah.
You expect them to be better at that kind of stuff.
I mean, it's stuff you can't predict. Like it was a land development deal. I mean, no one predicted that the housing market would crash. They wouldn't be able to sell this land to developers. So I mean,
Where's the market?
Texas City. It was right before they took this loan back in like '07, so it was before hike. So I mean, all these factors happen you can't have control over. It's just not tanked, and you got to stick it out. There's a loan that I sold. And when tits up, and people want help, I'm just gonna say, you knew what you're getting into, and you purchase a loan. We're gonna have to ride this out together.
You
Get through it.
consulted your lawyer when you.
You should have read the participation agreement. Yeah, you would have said it.
I agree with you. When I was thinking in Ball's class yesterday, remember when he was talking about the interest rate and the inverse relationship between short term and long term?
No.
Basically, he's saying nobody wants to borrow right now. Like that's
Everyone wants to borrow long term. No one wants to borrow short term. Everybody wants to
even
fix
then,
long term rates.
I mean, the 30-year fixed, it's got to be around 5% now, right?
Oh, it's like 4. It's lower than that now.
Yeah.
It's like 4. I think last week it was like 4.75. It's getting.
For 30 years?
Yeah, man.
That is unbelievable.
What would you lock yours in at? I think mine's like 4.875.
For 30?
Yeah.
So
Yeah, everyone
I
wants.
think it's going to stay like that for another year, which is perfect for me because that's when I'm going to get into a house.
Yeah. Everyone wants long-term rates, fixed long-term rates.
Yeah, I wish I
I mean, the first question they come in, they want 5-year fixed rate. Well, I'll give you a 5-year fixed rate that's going to cost you 8.5%, or we can do a floating rate loan with a floor of 6 3/4.
So you talking about commercial?
Yeah.
I would never.
I would never do a fixed rate loan unless I was getting a healthy spread.
30 years?
No, not 30 year. I would never do it. Yeah, I would do a balloon.
Yeah, 3 to 5 years.
Okay. Yeah, I was going to say. I've never heard of
Or unless you're going to go match fund, you go out to the Federal Home Loan Bank and you purchase the deposit to match offset it. But like Dexter said, so you put a heavy penalty in there for the borrower if he pays it off early. So, if it's a 5-year fixed rate, then they're going to get the charge. 7 3/4, 8.5%. Or they can go with a prime plus 1, probably 4, 6.5. Prime plus 1 puts up 4 1/4, and they have to go up 225 basis points to really start getting affected. So, I mean, it's that 225 basis points. That could be 2.5 years from now, depending on what the Fed does. I don't think they're going to raise rates next time. I don't think so. I think today they're going to. I don't think they're going to say for what's the key phrase they use? Remained unchanged for a unspecified time or something like that. I think they might say, they said that an article this morning about them saying that for a shorter time they're going to be fixing that.
I'm sorry, what was the very last part?
That they made a comment that the Fed might say that they're going to leave rates where they're at, but for a shorter amount of time, not for
Oh, really? So why picking that as 12 months?
I mean,
12 months, 6 to 12 months maybe?
I think they'll start raising.
I think everyone expects it's sometime in 11.
Yeah, they won't go.
But certainly they can't raise it that much. A lot of people thought it would be fourth quarter of
That's so sad, right?
I mean, we got 42. Increase it just a little bit. It's going to have negative effect on the market. Too fast.
I guess all the manufacturing reports came out last week, were all down. So those guys always wanted a higher rate, but don't know where to sell their goods.
No, we should probably just ask architects.
What's that?
He probably knows what's going on.
When we on the syllabus and we have multiple linear regression, when we do like stochastical analysis, how far are we going inside our means?
Well, no, that probably, we're going to do,
We're going to reject the
oh,
host.
wow. I'm just electrocuting myself here.
Are we going to reject the host? Or are we going to
That's
accept
right,
the
we're
host?
definitely going to reject the host. What is that? Every time I plug in there, it gives me some buzzy kind of thing.
I haven't seen that since 363.
Over here. All right. Yeah, I don't know what that was. All right, you ready? Now let's just pass this stuff. I just did this. Most of you have your book, but if you don't want to bring your book every time. I mean, it saves you from having to. You can leave your book at the end of the room if you want. Because the tables we have to have, right? So you go to Charles.
So what are we calling that to be for master?
Yeah, my name
Did you look it up? Right now we're not even. She just kind of.
I used to call Mr. Harwell, right? Master
Not really.
Harwell.
Kind of like the chapter 1.
Okay, how did I not have enough copies? How many people are there? 1, 2, 3. I made 18 copies and I don't have enough.
You don't ever know when and have a copy it real quick.
No, we can copy it.
Like I remember this is inside the curve here.
I can't believe it. I don't.
There's some more in the back. Right here.
Oh, there you go.
That's all inside.
So that's the original. Isn't that funny?
Oh yeah, because it's one half. That's inside.
I guess I can't count. All right.
And we said it counts.
That's right. That's what they call us at the bean counter. Wow. I must have made 16 copies. I don't know how I did that, or left the original in there. Okay. All right. All right, all that dead air out, they're going to cut that right out for you. So you don't have to that later. I'm afraid to turn it off. I know that you can turn it off and turn it back on. I just don't. I mean, I'm not taking a chance. I'm afraid if I turn it off, we'll never get it back on. And then it'll be... That's just sort of my experience with any kind of technology. Just leave it on. All right. All right, let's look at the notation up here. Right, the parameter, the Greek letter mu. And again, let's see if we can do this. Okay, you see the mu? It looks like that. It doesn't. I'm going to see if I can do a better one. That really is a little bit more like it. It's dependent entirely on your font, right? Mu it's mu, of course, the Greek letter mu, which represents the population mean, right? So what we want to know is mu. What we're going to settle for is, in this case, y bar. It could be x bar. It could be d bar, whatever the variable you call it, right? And the bar meaning it's the average, right? That's the sample mean. Okay, so these are all sample statistics, right? So a statistic is always a characteristic of the sample. A parameter is always a characteristic of the population, right? So population parameter, sample statistics, okay? The population mean, mu, the sample mean, x bar, y bar, whatever it happens to be, right? The population variance is sigma squared. Okay. Now, not to be confused for those of you who can't remember statistics very well. There's right sigma. We have two. When we use the notation sigma in Greek letters, just like in Latin letters, they have two different kinds. Right. We have lowercase and uppercase, whatever we call those. With Greek letters, we have what? We have script letters, and then they have block letters. So the script letter sigma looks like that. Right? The block letter sigma looks like this. This means to some, and I kind of made that too. If I can erase this up. I made the little tail a little long, didn't I? Okay. I can remember when I was taking, I think it was finance, and our professor he made sigma like this. Let's see if I can do it. All right. It was almost like that, and I thought, whoa, that's recognizable. Yeah. So it should look like it's like a circle with a little tail, and it really is kind of straight, right? Not so much. Anyway, it's just a little bit more like that. All right. Again, the notation, the population, the true variance is sigma squared. Our estimate for that is s squared. The standard deviation is sigma, right here. This is what we want to know. What we're going to settle for is S. That's our estimate for the population standard deviation. It's the sample standard deviation, which is S. All right? No, come on. What are we doing here? I wrote on it, now we can't advance. Any trouble? Press it up here. We don't know what we're going to talk about. Probability. Are you guys excited? The most fascinating branch of mathematics is probability. All right. Now, we're not going to talk about elementary, although probability really is not bad. Remember, you can write in terms of, do you remember, have you covered probability before in some class? And you remember it well? All right, now, probability is really basically it's not bad, right? You can learn the basic rules for probability. Learn the additive rule, right? The multiplicative rule. The additive rule is for calculating unions, the multiplicative for calculating intersections, right? Anyway, once you calculate probability, if you can calculate it for 2 events, you can calculate it for 45. You just follow the rules. You just go all the way through following the rules, right? All right, but probability, in essence, probability distribution is what bridges the gap between descriptive statistics and inferential statistics, right? So we can take a data set and we can calculate descriptive statistics and we can describe the data we collected. But if we're going to want to make inference using that sample statistic to make inference about the population as a whole, we base that on probability, our understanding of probability distributions, right? So that's what bridges the gap between descriptive statistics and inferential statistics is probability. Now, we use probability, right? We assess ahead of time, depending on if we're going to come up with a confidence interval, how confident we want to be. We determine what that is, right? Say we want to be 95% confident. We're coming up with a 95% confidence interval for some parameter. So we determine that, right? It has to do with how in terms of controlling the goodness of our inferences. Now, we have two different kinds of probabilities, obviously. The probability that we're right and the probability that we're wrong. Now, these are all a priori probabilities. What's that mean? What's a priori? Well, they don't teach Latin anymore, right? What does a priori mean? Before, okay? So, before I take my sample, based on the size of my sample, the standard deviation, the variability of the distribution, and so forth, I can tell you how to calculate using the appropriate numbers, calculate a 95% confidence interval. What does that mean? The probability that our parameter is included in that interval is 0.95. The probability that it's not 0.05. That's before I take my sample, right? Because once I take my sample and calculate my statistic and come up with my interval estimate, then either the parameter's in there or it's not. Do you agree? Okay. So after the fact, ex post facto, after the fact, then it's either in there or it's not. That probability that we're talking about is a priori. It's before we take the sample. Okay, but it's based on those numbers. Assuming we take a sample of this size, the probability that this interval will contain the true parameter is 0.95. Okay? All right, so probability is used in measuring and or controlling the goodness of our inferences. We have the probability of being right and also the probability of being wrong. Okay, probabilities must be what? Between 0 and 1. I always like it when somebody goes, I'm 110% sure that something. No, it's not. The probability that I will lose a lot of money when I go gambling is 150%. No. Probabilities are between 0 and 1. There is, we use probabilities when we have uncertainty. Do you agree? When we have uncertainty? If the probability is 0, there is no uncertainty. What does it mean if the probability is 0? It absolutely will not occur. Now, sometimes we have probabilities 0.0000. What's that mean? Well, rounded to 4 decimal places, the probability is 0. Does it mean that there's not a chance that will occur? No, it means it's unlikely. It's just very, very small. In other words, there are times when they round to 4 decimal places and you have 0.0000, meaning it's unlikely, right? It's not truly 0. There are times when we have probabilities that are truly 0. That means they definitely will not occur. If the probability is 1, what does that mean?
10%.
Definitely will occur. Probability is 1. Then sometimes, again, we round, right? We round to 1, suggesting it's very likely, but it really is 0.99999. Something or other, right? It's a possibility that it won't occur, but very, very small. All right? So, now most of the time our probabilities fall between 1 and 0, meaning we have uncertainty about whether or not a particular event will occur. But again, probabilities are values between 0 and 1. Inclusive. That means including both. Okay, now let's talk about the normal distribution. Are you excited? Do you remember the normal distribution? Right? The Gaussian distribution. What is the normal distribution? Lots of things we consider to be normally distributed. And what does that mean? It's a bell-shaped curve, right? It is a symmetrical distribution. What'd you say?
Like you can apply empirical rules to it.
That's exactly right. You could imply. Okay, let's see. He's talking about the empirical rule, and we'll talk about that in just a minute. The normal distribution is mound-shaped, right? It is symmetrical. What does that mean?
Centered. It's not skewed. It's centered.
That's right. As opposed to asymmetrical. Asymmetrical means it's not symmetrical, right? So a symmetrical distribution is this. This is the first, when you talk about it, I think it's in physical science, right? They talk about symmetry. If you cut something in half, we're going to talk about animals, right? If you cut something in half right down the middle, and one side is a mirror image of the other, right? That is a symmetrical distribution, or whatever it is. It has symmetry, right? So what happens is the left side is the mirror image of the right. For every value on the left side, you have an offsetting and corresponding value on the right. Okay, so what happens is this. The mean, the population mean, mu, is in the center of the distribution. If you have a symmetrical distribution, the mean and the median are the same value. right? So what happens is the gravitational center is equal to the positional center if you have a symmetrical distribution. Now, there's lots and lots of symmetrical distributions, right? You can have a uniform distribution, right? That's symmetrical. You could have a bimodal distribution that is symmetrical. Lots and lots of symmetrical distributions. And how do you know if it's symmetrical? You cut it in half right down the middle. If one side looks identical to the other, then it's a symmetrical distribution. All right? It's not skewed at the point that they made in the back, right? So it's not a skewed distribution. All right. So the normal distribution is symmetrical, right? Total area under the curve is 1. So if it's symmetrical, half or 0.5 to the right of the mean and 0.5 to the left of the mean. 50% of the values are going to be above the mean, 50% of the values will be below the mean. Now, by definition, the normal distribution is asymptotic to the horizontal axis. What's that mean? It's an asymptote on both sides. It will approach but never touch the horizontal axis. So, in theory, the normal distribution goes what? From negative infinity to positive infinity. Now, some things we assume to be normally distributed, like IQ scores, obviously the values don't go from negative infinity to positive infinity. Do you agree? All right, that's just in theory, because we assume a lot of times. We will talk about, and let's talk about this real quick. We have two different types of data. We have discrete data, and we have continuous data, right? Or random variables. Discrete, random variables, and continuous. What does that mean? If we're talking about the number of siblings that you have, that is discrete. Do you agree? In other words, you have no siblings, you have one sibling, you have two siblings, 3, 4, 5, whatever. Can you have 1.5 siblings? No. Let's say cars. Can you have 1.5 cars? I mean, I know. Yeah, somebody knocks off the back end of it, then you have 1.5 cars. I'm just talking about, how about this? You are a doctor, and you have patients coming in to see you. The number of patients that you have in a day have to be integer values. You either have no patients, you have one patient, you have two, but those are discrete values. You agree? This is a discrete random variable. There are gaps between the values that the random variable can take on. Do you agree? A continuous random variable, on the other hand, can be represented by a curve because, by definition, a continuous random variable can take on any value in a range of values. So we use curves to represent the distribution of those random variables. Number of siblings that you have would not be represented by a curve, right? You'd have lines. You'd have 0, and the height of the line would be the frequency that it occurred, that we found someone who had no siblings. 1, there'd be a line. In other words, there'd be a line, or a bar, or something that represent them, but there'd be gaps in between, right? You understand what I'm saying? The difference between discrete and continuous. All right, now, sometimes we use discrete random variables and talk about them being normally distributed. How is that? Dollars and cents. Is that discrete? Yes. Why? Because that's not... If we talk about a continuous random variable can take on any value, can dollars and cents take on any value between, say, $100 and $200? No. It can take on only dollars and cents. Once you get smaller than like half a cent or a tenth of, right, 100th of a cent and so forth, it doesn't take on those values. But what happens is this. Because it can take on so many values, and let me just show you right here. We're talking about a discrete distribution, and depending, like you was talking about 0 siblings, 1 sibling, 2, 3, 4, and of course the height of this is going to be the frequency of x, right? So what happens is we have the height, right? This is a discrete random variable. They're represented like there are gaps between the values that the random variable can take on. That's discrete random variable. This is continuous, one of many continuous random variables. All right, but it's represented by a curve. And everybody, you see the difference between the two? So what happens is if I have dollars and cents, in fact, I have what? I have a whole bunch of lines real close together. I'm not going to draw them on top of there, but you see what I'm saying? If we're talking about dollars and cents, we have so many lines that it's just in essence a continuous distribution. We're measuring like $100.01, $100.02, $100.03. You see what I'm saying? So I'm making an assumption here. It's really a discrete random variable. We're pretending that it's continuous. All right. All right, so we have a continuous random variable. We're going to say IQ scores are normally distributed. A bell-shaped curve or the normal distribution means what? We have the mean, which is in the center of the distribution because it's symmetrical, right? It's in the center of the distribution. Half the values are less than the mean, half the values are greater than the mean. The closer we are to the mean, the more likely it is that we're going to have values. Do you agree? As we get further away from the mean, the more unlikely it is that we have values, right? In other words, the probability that we get a value over here is less likely than over here, right? The closer we are to the mean, the more likely it is that we're going to get values. See, the height is the frequency. All right? So we consider things to be normally distributed that typically fall close to the mean. Right? So you normally get values close to the mean as you get further from the mean, and you should expect it to be in both directions, right, for it to be normally distributed. So the reason we use the term normal is many things have that distribution. Here's the center of the distribution. Most of the values are close to the center or are going to take on values that are close to the mean. As you get further from the center, the less likely that is to occur. Okay, so IQ scores. The average IQ score is probably 100, right? We take the middle age to the chronological age, multiply by 100. So if that value, if those numbers are the same, the value would be 100. Your IQ score would be 100. Your middle age and your chronological age are the same. Now, we have people who have IQs that are less than 100. The further you get away from being, and others, the smaller that IQ gets, the less likely it is to occur. Same thing for on the upper end, right? As you get further above 100, the less likely it is to have people who have IQ scores that high. Does everyone agree? So the normal distribution, mound shape, and so forth. All right. So 50% of the values are to the right, 50% to the left. The mean is in the center of that distribution. All right. Let's see. And the point that he was making a while ago, we can use the empirical rule, right? We have several theorems that have been that people have come up with over time. It's amazing to me because if you can imagine coming up with a normal distribution or coming up with the central limit theorem or the empirical rule before they had calculators, I'm telling you we're talking about people who worked years and years studying these distributions. Most of them were in the 17 and 1800s, right? They came up with these probability distributions. Anyway, the empirical rule, which applies only to the normal distribution, tells us what? Do you remember the empirical rule? Approximately 68% of the values will fall within one standard deviation of the mean for any normal distribution. Approximately 68% of the values will lie one standard deviation, and I'm not sure. I apologize. I probably should look through my thing. I'm not sure that the empirical rule is on here. All right. All right. For any normal distribution, okay, the empirical rule. Okay, it includes approximately 68% of the observations. Mu plus or minus 2 standard deviations includes approximately, somebody remember this one? This is the one we use most of the time. 95%. Approximately 95% of the observations will lie within 2 standard deviations of the mean, and virtually all of the data is included within 3 standard deviations of the mean. 99.7%. All right, so if you think about, here's mu, right? So let's just make up a value. Let me see if I can do this. All right, now. So you have mu minus sigma, mu plus sigma. So 0.68, 68%. Is that right? Yeah. Yeah, I'll check. I don't usually teach the empirical rule. It's been a while since I thought about it. Okay. 68% of the values will fall within one standard deviation of the mean. I know I didn't draw that to scale. All right, so what that means is 68% is in the center, right, and so forth. So 0.16 over here and 0.16 over here. Do you agree? All right. And then, of course, we could do plus or minus 2 standard deviations. Mu plus 2 sigma would be someplace over here. And in that area there, .95 approximately, right? So 0.025 in the tail over here, 0.025 in the tail over here. All right, for any normal distribution. Only for normal distributions. Only for normal distributions. The empirical rule is only for the normal distribution. All right, now. So what is that? Go ahead.
How did you get 195 out of 116, 168, 116?
No, I didn't. It's two different pictures, right? The first rule says mu plus or minus 1 standard deviation, so that's the 68%. So if you're talking about what we know is approximately 68% of the values for any normal distribution lie within one standard deviation of the mean. So if we knew mu and sigma, let's say mu was 100, sigma was 5, we say have 100 minus 5 is 95 to 105, approximately 68% of the values will fall in that interval if it's normal. Now, the second rule, this is just empirical rule, it's like a rule of thumb. It's based on the distribution. Mu plus or minus 2 sigma. So if mu was 100, sigma was 5, 2 times 5 is 10, 100 minus 10, 90, 90 to 110, 95% of the values are going to fall in that interval. So I was trying to draw another picture, that's the reason I used the next number. I mean the other color. Okay, it should have been on different ones. Sorry about that. Yeah, it doesn't make as much sense if you look at it that way, right? So if I erase it, let me do it this way. See, now I'm only talking about the other. I should have just done it separately. All right, so you have mu plus or minus 2 standard deviation, 95% of the data falls in that interval. All right, and then for 3 standard deviation, 99.7%, what does that mean? That means most values for a normal distribution will lie within 3 standard deviations of the mean. Does it mean I can't get a value that lies outside of 3 standard deviations? It's just not likely, right? But what did I tell you? The distribution goes what? It's asymptotic to the horizontal axis, so it goes from negative infinity to positive infinity, right? So, could I get a value that was, if I have a normal distribution, could I get a value that's 10 standard deviations above the mean? Sure, just not likely, right? The probability is very, very small. All right, does everybody understand? Now, based on our knowledge of that distribution and the fact that most values fall within 3 standard deviations of the mean, if I assume a value for mu, and I take a sample and get a value for x bar that's significantly away from that value, that estimate, a long ways off, I might think, gosh, mu, maybe I'm wrong about mu. Maybe it's not this value. I got a value for x bar that's way, way out there, a lot larger than mu. I don't think mu is right. I think what I thought mu was is no longer, it's no longer that value. That's how we make decisions in statistics. Based on probability distribution and our sample statistic, we're going to decide, gosh, what we used to think about the population mean may or may not be true anymore. Does that make sense? That's how we do it, based on probability distributions. Okay, based on probability distributions, we're going to decide what we believe. All right, let's see where we are now. Okay, there we go. The common is the normal distribution, the bell-shaped curve, right? It is symmetrical about the mean. Under the area under the curve is synonymous with probability, right? And when I said the sum of the area under there is 100% of the values fall under the curve, right? All right, the total area is 1. The standard normal. All right, now we're going to talk about the z. Do you guys remember what a z is? Kind of a z-score. It's a measure of position, right? It's similar. What about percentile rankings? When you took the GMAT, right? Or if you did take the GMAT. Some people took the GMAT. I had to take the GMAT when I went to school, right? Okay, so the GMAT, and you get a score. Do you get a percentile ranking? All right, what does the percentile ranking tell you? Where your score lies relative to what? Everybody else. Everybody else who took the test, right? So we've talked about measures of central tendency, which is one number typically that describes the center of the data, right? What is the typical value? That's one value that describes, it's an attempt to get one number to describe the entire data set, right? The standard deviation, again, is one number that describes how spread out that data set is. Now we're looking at it differently. Now what we want to know is, assuming that we know where one value is, we want a number that describes its position. Or we want the value that lies at the 75th percentile. So this measure of position is going to be, this is a different kind of measure, right? This is saying at this point in the distribution, what is the value? Or here I have a value, where does that lie relative to the other data points, right? All right, so let's talk about the z. If you remember, I'm afraid to bring up a blank screen for fear I'm going to get messed up. I'm tempted to try it. All right, I'm just gonna write on here. Okay, what is the z? Do you remember when you calculated the z and it was x minus mu divided by sigma? That's the typical z. Do you remember that? This is a standardized score. Okay. And let's just make something up. Let's talk about IQ scores. Okay, let's talk about IQ scores. Let's say the mean IQ score is 100. And let's say the standard deviation, gosh, I don't know what that'd be. Let's think about that. Let's say 15 is the standard deviation. I'm trying to make it kind of realistic, right? All right. Now, let's say that let's say someone in the class has an IQ score. Somebody tell me, the person next to him, what's their IQ score? Be nice. Okay, someone said 130. Okay, I want to find a z-score. What I want to know is a measure of precision, right? If you have an IQ of 130, where do you lie relative to this? The z-score is going to tell you this, okay? And the z-score, we're going to talk about it in just a minute. So we take 130 minus the mean, which is 100, right? Divided by the standard deviation, which is 15. Now let's talk about this. In the numerator, what does the z tell us? How far is the value from the mean? That's the distance, right? That's the distance of the observed value from the mean. Now, what are we doing? We're dividing by the standard deviation. Okay, let's think about it this way. If I told you that the z-score tells you the number of standard deviations that the value is from the mean, how do I do that? I look at the distance, and then I put it in units of the standard deviation, right? I'm dividing by the standard deviation because I want to know how many standard deviations. If we're talking about IQ scores, what would you like to be? Many standard deviations above the mean, right? If you talk about IQ scores, everybody wants to be smart, I assume. That would be the preference, right? Now we're talking about golf scores. You would like to be 2 standard deviations below the mean, right? Because you're talking about a golf score, you want it to be small. All right, so we calculate this value. 130 minus 100 is 30, divided by 15. We are what? 2 standard deviations. Okay, the z-score is 2. In units, it's 2 standard deviations above the mean. Do you agree? How likely it is I'm going to get a value up there?
%.
95 between, and then we're back in the tail. No, Brian's close. What is it? What's your name?
My name's Andre.
You already lost your name. Second day, you're in trouble.
Adam.
All right.
Messed up.
Did Brian take it?
Brian took it over.
All right. Andre, did you make that up, or is that really your name?
No, it's really.
I was just wondering. I don't know, you kind of strike me as a practical joker or something. I would make sure. Okay. Miss Autumn Miss California gets that shirt on. All right, now, you answered it a while ago. You said about 95%, right? Now, remember, you guys, he's saying, and Brian almost got it right, if this is mu plus 2 sigma, mu minus 2, well, I'm just saying he's close. At least he understands the concept, right? I said 95% fell within 2 standard deviations of the mean for the empirical rule. 5% is outside, right?
2.5.
So, yeah, 2.5 is over here, 0.025, and 0.025 in that tail, right? I screwed up on that. Somehow. Okay, what I said was, okay, so 2 standard deviations above the mean, if we're talking, these are values, if the z, this value here, if it's 2 standard deviations above the mean, the z is equal to 2. If it's 2 standard deviations below the mean, the z is equal to what? Negative 2. In other words, the z-score tells you the number of standard deviations you are from the mean. If it's negative, it means you're 2 standard deviations below the mean. If it's positive, it means you're 2 standard deviations above the mean. Now, Brian, what percentage of the values are below the person who scored a 2 on an IQ score? It's this value plus this, isn't it? It's 97.5 is below. Only 2.5% of the people are above you. All right? Or approximately, right? All right, so you understand now what is the z-score? So what we use a z-score to do is say how many standard deviations are we from the mean. All right, why is that important? Well, the empirical rule. If we're talking about a normal distribution, and what you'll find out is, guess what? X bar is normally distributed, as are most of the statistics we're going to talk about. Okay, that's the reason we're so interested in the normal distribution. All right. All right, now we're going to talk about the z. We can convert any normal distribution to what we call the standard normal, which is the z, right? How do we do it? We use that formula, z equal x minus mu divided by sigma. We can take any normal distribution with a mean of whatever and a standard deviation of whatever and convert it to the standard normal by using that formula, right? Now, what happens is, as you take the value minus the mean, where do you move the mean back to? You move the mean back to 0. The standard normal, you see what I'm saying? If I take a value and subtract the mean from it, I'm moving the mean. Like if we have a normal distribution that has a mean of 100, your IQ scores, and we convert all those values back to a z, we take each of the values minus the mean. When you take the mean minus the mean, what do you get? 0. So the distribution of the standard normal has a mean of 0. All right, and a standard deviation of 1. All right. So what happens is the standard normal distribution, and we usually use this notation like this. We say z is distributed normally. Okay, that means whatever the random variable is, z, and that notation, which was kind of funny there, but it just, the little like that means it comes from a known distribution is what it means. The N stands for the normal distribution. If we're talking about the Poisson or the binomial, we'd use a different notation. We're using N for normal. And then in parentheses, we're going to use we're going to put the parameters of the distribution, typically mu and sigma squared, right? So Z is distributed normally with a mean of 0 and a variance of 1. The standard deviation and the variance are both going to be 1, right? Because 1 squared is 1. All right? So if we have X is distributed normally with a mean of 100 and a variance of, we'll say 15 squared because we said the standard deviation was 15. This could be the distribution of the IQ scores. I can take this entire distribution here and convert it to the standard normal using my formula. Again, what is my formula? Z equals, for every value X, we subtract the mean, divide by the standard deviation. Every value in that IQ score can be converted to the standard normal, and then we have the same, we can convert everything to the standard normal. And the reason we do it is this. We have a probability distribution for a normal distribution. We have infinite number of normal distributions, right? We have normal distributions. Mu could be any number, right? It's a continuous distribution. It could be any number. Sigma could be any number, right? What we want to do is convert them all to the standard normal so we can use one probability table. So we convert everything to the standard normal. Then we convert the values, and for each individual value, it'll give us a Z value, which tells us how many standard deviations it is above or below the mean. We use that value, the Z value, to find probability. All right, so it just makes it easier for us. We convert all normal distributions to the standard normal so we can calculate probabilities. Come on, do you have a question?
Too many. Too good.
Can you articulate one? I don't know. I've been there before. That's right. I felt like that before. Like, I'd like to ask you a question. I'm not sure how to say it. I don't understand anything you just said. No. This is sort of the theory behind it. Is it completely necessary that you understand it completely not to be able to do the problems, right? It just is and it is. Number one, we use notation, which is not familiar to you. We talk about probability distributions that just seem like blah, 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 right? It's like it doesn't have really any good meaning to you. But it doesn't mean that you can't understand and use statistics. And why? What am I having to do here? Okay, I did this like they said. That's plugged. It's a thing. Shut that. Maybe that's better. Oh, look at all the stuff I wrote on there. How about could I advance my table?
Take the cursor down to your arrow to the next slide and it works.
I know I did it. To see this? There. Thought we were stuck there. We're going to be in trouble. All right. The standard normal distribution, the notation Y is distributed normally, and that's just the same thing except they're calling Y's down there, so it's the mu sub Y and sigma squared sub Y. All right. Same notation. Don't worry about it. Same thing down here. The Z, we're going to calculate. We're going to take for every value in that distribution, whether it's an X, a Y, a Z. I guess we don't want to use Z because we're talking about converting them to a Z, but you can use any variable, obviously, except for Z in this case, to represent the random variable. But again, we convert those all to the standard normal. All right. Oh, wow, we're trying to T. Let me look just a second what's on here. Just a second. All right, let's go back. All right, let's say, because we didn't really talk about the central limit theorem, and I'm not sure exactly where it falls in this review, but let's just for just a second, and maybe this will make it a little bit more understandable to you. Maybe it'll just confuse you all more. That's not my goal. But let's say that we were talking about ages. Okay, we were talking about ages. Let's say that we are trying to determine for some large population, right, what is the average age of students enrolled. So let's just say that we're enrolled last spring at San Houston State University. On the 12th class day, what was the average age of students? Because I'm interested to see, again, if we have more non-traditional students or whatever. Okay? All right, so that's a huge population. Do you agree? But let's just say, and when I talk about that, it seems like it's almost in the abstract, right? I want to know the average age. What am I going to do? I'm going to take a sample of whatever size, and then I'm going to calculate the mean of the sample. And I'm going to use that sample mean to estimate or test the value of the true mean age of all the students. All right? Now, let's think about a small finite population like this classroom. Okay? So let's just say in this classroom, if we added up all your ages and divided by 17, right, we should get the average age of the students in this classroom. Do you agree? All right, so, and let's just make up a number. What do you think the average age is?
29.
29. We'll say it's 29. All right, now, so mu is 29. Mu is 29. Now, let's just pretend like it is in the real world. This is a population we don't have access to. We can't access every element of the population. So what do? We take a sample, right? So let's say we're going to take samples of size 3. How many samples of size 3 are there in here? There's a bunch. 1, 2, 3. How many? So 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. It's a county room. Okay, but no. Every possible combination of 3 people. It'd be the counting rule, right? I'm going to put 3 people. Well, it doesn't matter, but a bunch of them, right? There's a bunch of them. Okay? There's lots of them. Like I said, it could be these 3 people, or these 2 with her, or these 2 with her, or these, right? And then we go through all other combinations. So how many possible samples of size 3? It doesn't matter, but there's a lot, right? So let's just say we take all the samples of size 3. Could we do that? Yeah, it would be tedious, but could we do it? Yes. And for every sample of size 3, we calculate the average age. So what do we have? We have a whole bunch of average ages, a bunch of X bars or Y bars or whatever you want to call them. You agree? Sure. Now, those are samples. Those are sample means, right? For every sample of size 3, we have a sample mean. Now, those sample means come from some distribution. Do you agree? Yes. All right, so we know that X bar, Y bar, whatever, the sample mean, is a random variable. It's going to vary in value, comes from some distribution. All right, now, the central limit theorem tells us this. If we take the mean of the mean, this is mathematically true. Let's just mathematically, not even the central limit theorem. If I calculate I take all the samples of size 3 and calculate the X bars, and then find the mean of the means, what is it?
Calculation mean.
29, that's right. It's 29. Is it not mathematically? We know that's true. So the mean of the means is 29. Now let's think about that. You remember back to the way back when you talked about, when you were first talking about probability distributions, and it used the term for the mean, the expected value? Like the binomial distribution, the Poisson, they talk about the expected value, which is the mean. It's like the expected value when you roll 2 dice is what? 7. 7 is the expected value, right? All right, so, and that's because it's more likely it would occur, right? That's the expected value. That's in the center of that distribution, okay? And if you add them up, all possibilities, then the expected value is 7, the mean. All right, so when you take a sample and calculate X bar or Y bar, the expected value is mu. It comes from a distribution in which mu is the center of that distribution. X bar, the center of that distribution is mu. So that should make you feel good, right? I told you were guessing, but guess what? It comes from a distribution in which the expected value is mu. All right, now, does it have more or less variability than the original distribution? In other words, the original distribution would be all of your ages. There's less variability in the means. Why is that?
Because the mean of the means group.
Because what happens when you calculate a mean? These three ages.
You're averaging an average.
That's right, so you're getting closer to the center, aren't you? It'd be like if you put my age in with two of you, right? I'm 54, if my age by itself, I'm way out in the tail of that distribution, right? But if you put me with two other people, what happens? Well, it brings it down a little bit, doesn't it? It's closer to the center. If you put me, and the larger the sample, what happens? The less influence I have, the closer to the center will we calculate the mean. Does everybody agree? So what happens is this. X bar comes from a distribution that will have a mean of mu from the original distribution. The standard deviation, we call it the standard error of the means. Let's see if I can do this. So we have X bar is going to be normally distributed. Actually, I didn't say that yet, but we talked about it. All right, so it's the mean of the sample means. Those are the X bars. The mean of the sample means is mu from the original distribution. We'll just say mu. The standard deviation, I'm going to abbreviate this, the standard deviation, and they call it the standard error of the means. The standard deviation of the sample means is equal to sigma divided by the square root of n. So the original distribution has a standard deviation of sigma. The standard deviation of the distribution of the sample means is sigma divided by the square root of n. So what happens as n gets larger, that value gets smaller and smaller, right, by a factor of the square root of n, right? So it gets smaller. As your sample size increases, the standard error of the means gets smaller and smaller. So we have less variability in the distribution of X bar than we do in the original distribution of X. Does everybody understand? All right, so we have this one distribution, and we don't have to just be talking about this class. I just wanted you to understand. You have a population with a mean mu standard deviation sigma. You sample from that population and you calculate an X bar. It comes from a distribution of possible X bars that has a mean of mu, same mean. It has a standard deviation that is smaller, because again, we're calculating mean, so it's moving toward the center. It's smaller by a factor of the square root of your sample size. All right, so the bigger the sample, the less variability you have. All right? Now, the next thing is, and I really should do it like this. I should put this up at the top. We'll call this, sorry. This is the central limit theorem. All right, number one, the mean of the sample means is mu from the original distribution. The standard deviation, and it's a standard deviation calculated like any standard deviation. They just call it the standard error of the means because anytime you calculate the standard deviation of a statistic, they call it an error. Why do you think that is? Because when you calculate a statistic, what you really want to know is the value of the parameter, right? You're trying to estimate or test the value of the parameter. So as the values fluctuate around the true parameter, it's regarded as an error, right? Because they're estimating mu, so as they fluctuate around the actual value of mu, it's considered an error. So they call it a standard error. But it's still just a standard deviation calculated in the same way, all right? So the standard deviation of the distribution of the sample means is sigma divided by the square root of n, meaning it's smaller. All right, now the next one is if the original distribution is normal. If the original distribution is normal, I'm going to abbreviate distribution, is normal, but nominal, right? Okay, let's see. The distribution of the sample means, and I'm going to see, will always be normal. Regardless of the sample size. What does that mean? That means if you have normality, you keep normality. If you're talking about IQ scores, they're probably normally distributed. So you sample from that distribution. You take a sample of 30 of people with IQ scores or 30 IQ scores. You have, when you calculate X bar, that comes from a distribution that's normal. You started with a normal distribution, you still have a normal distribution. If you take a sample of 2 and calculate X bar, Y bar, whatever, you still have what? It comes from a distribution that is normal. Why? Because we started with a normal distribution, we will keep a normal distribution. Now, that really is not very useful to you. Why? If we don't know anything about the population, we certainly don't know if it's normally distributed. We might think it is, we might be able to guess that it is, but do we know it? No. So the fourth thing down here is the most important thing. Regardless of the shape of the original distribution, that means what? It could be skewed to the right, skewed to the left, it could be a uniform distribution, it could be distributed as a binomial distribution, it could have any distribution. Regardless of the shape of the original distribution, the distribution of the sample means will be approximately normal if your sample size is large. And what is large? 30. That's a rule of thumb, 30. Okay? Regardless of the shape of the original distribution. Regardless of the shape of the original distribution. The distribution of the sample means will be approximately normal if the sample size is large. And we normally say n is greater than or equal to 25. Well, 30, I'm sorry. We'll say 30. And really what happens is this is kind of a rule of thumb. We're going to say 30. In fact, for most distributions, once you get to a sample size of about 10, you have a normal distribution. You start sampling. And this is how somebody figured this out, is they actually had to have a distribution of numbers. And they had to take all possible samples of size something from it. And they had to plot the X bars. And this was back a long time ago before they had calculators. They did this by hand. And again, it took them years and years to calculate this. To figure out the normal distribution, it took a long, long time. Okay? All right, so the central limit theorem. Okay, the central limit theorem tells you this. Number one, if you have a distribution of sample means, the mean of the distribution of the sample means is mu from the original distribution. I don't know how I took off that top part, but I obviously did. You can still see it, I guess. All right. The next thing is the standard deviation is going to be smaller, right, by the factor of the square root of n from the original distribution. Everybody understands we're talking about we have one distribution, whatever it happens to be. If we're talking about IQ scores, your ages, or whatever it is. This is the original distribution, right? Those are the x's. If we sample from this distribution and calculate x bar, it comes from a distribution of x bars, right? And so this is about the distribution of the sample mean, all right? The most important thing is here. If, regardless of the shape of the original distribution, x bar is going to be normal if the sample size is large. So what do? You want a normal distribution. You take a sample size of at least 30. When you calculate x bar or y bar, the sample mean, you know it comes from a distribution that's normal. Why do we care? Because to be able to make statistical inference, we have to know the probability distribution of the statistic. Most statistics are distributed normally, which is great. Because we can use that probability distribution to calculate, right, to make our, and we have to know that we have to have a probability distribution to come up with our statistical inference. All right. Let's see if we can move on. All right, now, the Z and the T distributions are tabled in your text. Okay, these tables will be used in the construction of confidence intervals and to find the critical values in hypothesis testing. We have to have, remember I said you have to attach probability whenever you do statistical inference, okay? All right. We're going to look at that in just a second. Okay, we're going to talk about two types of statistical inference. We have estimation and hypothesis testing, right? And today we're going to talk about estimation. All right. Very simple. Two types of statistical inference. In estimation, we're trying to estimate the value of the parameter. So you run a restaurant, you want to know how many T-bone steaks you're going to sell next week. You want to estimate the number of T-bone steaks you're going to sell next week. How do we do that? Well, we look at data from the past, probably. We might look at, if we're talking about the entire week or however often we buy steaks, right? We try to estimate per day, and then we come up with our estimate for the week. All right? Now, let's say you want to estimate the average amount spent for lunch at your restaurant. All right? We're going to estimate the average amount spent at your restaurant for lunch. We come up with we take a sample, calculate the amount spent for one particular week or whatever. We use that as our point estimate to estimate the true number or true amount spent, the true average amount spent at your restaurant for lunch. Now, what happens is this. You have a brother, he opens another restaurant. On average, the patrons of his restaurant spend on average $6.50 for lunch. Now, you don't really care on average how much people spend at your restaurant. All you want to know is what? It better be more than $6.50 because you'll never hear the end of it from your brother. All right, that's hypothesis testing. In hypothesis testing, we really don't care about what the average is or the mean is. We want to know how it compares to some standard. Is it more than your brother's average amount spent? Is it more than it was last year? Is it more than your competitor? Do we now have a mean age that's higher for college students than it used to be because the economy is in a bad way? More people are returning to school. You see what I'm saying? We have some hypothetical or hypothesized value for the parameter. The average age of students in college used to be this. We want to know now, is it greater than this? All right? If we don't have any idea what it used to be, then we might just estimate what it is based on a sample. Okay? But two types of statistical inference. We're either going to estimate the value of the parameter. We use a point estimate, which is the corresponding statistic, plus or minus some number, and we're going to come up with an interval estimate for that parameter. Okay? Hypothesis testing, we have some preconceived idea about the value of the parameter. We either think it's equal to that value, not equal to that value, greater than or less than that value. And that's what we're going to do in a hypothesis test, is test that. Okay? All right, we're about to do something. Maybe you can slap your neighbor to keep them awake. Sorry, I'll just slap you. You look like you're about to pass out there. All right, estimation, our goal is to know the value of the parameter. We come up with a point estimate. What is our point estimate? What is our point estimate? It's always the corresponding statistic, right? So if I'm trying to estimate mu, my point estimate is y bar, x bar, whatever. It's the sample mean, all right? If I want to estimate the population proportion, my point estimate is the sample proportion. If I want to estimate the population variance, my point estimate is the sample variance. All right, you got it? Now, the interval estimate, if we come up with, if I said I took a sample and the average age of students was 25 years, is that my estimate? You guys think about this. If I say the mean age of the class was 29, if I take a sample of 3, add up those ages and get a sample mean, do I think it's going to be 29, the mean of their ages? Any sample of size 3 in the class, do I think the mean age for that sample of 3 is going to be exactly the population mean? No. Do I think it's going to be close? I hope so. So, I'm going to estimate mu now. I take a sample and calculate x bar, y bar, our sample mean. Do I think the sample mean is exactly equal to the population mean? No. I hope it's close. So what am I going to do? The probability that our sample mean is equal to the population mean is almost 0. Okay? So, that stinks. I don't want to have an estimate that is not likely to include my parameter. What am I going to do? I'm going to come up with an interval estimate. So, I take a sample, I calculate the sample mean, I get the number 26. I think it's about 26, the population mean. So what I do is I come up with, based on my probability distribution, I'm going to add and subtract some value to 26. We'll say it's 4. So 26 minus 4 is 22. 26 plus 4 is 30. My interval estimate is 22 to 30. Does it include the population mean? Yes, it does. In most cases, it will include it, right? Depending on how confident you want to be. How many standard deviations are going to go on either side of your point estimate. All right?
That would represent 68.
For the normal distribution, if I went 2 standard deviations on either side of the mean, it would include 95% 1 standard deviation, which we almost never use 1 because it only includes 68%. We typically want to be more confident in that.
Okay.
So we typically would want to be about 95% confident. We would go about 2 standard deviations on either side of that point estimate. And that way the probability would be about 95%.
But for the 22 to the 30, that would have been just 60. Right.
Well, I said add and subtract some number. What I actually been talking about is a certain number of standard deviations. In other words, I'm going to add and subtract something, right? It looks like this. We take our point estimate, which is x bar. I guess I can't use that color. I think red will show up. Okay, so I take my point estimate, which is x bar. I'm trying to estimate mu, okay? I'm going to add and subtract, and actually what I'm going to do is I'm going to add and subtract a z value, which is the number of standard deviations, times guess what? The standard deviation. So, if I use 2 as my z, or approximately 2, what's going to happen? I'm going to go 2 standard deviations on either side of my point estimate. The probability that mu will fall in that interval is about 95%, because I went 2 standard deviations, because x bar is normally distributed, and that's the standard deviation of x bar. This number is the standard deviation of x bar, right? So I'm going to pick a certain number of standard deviations based on how likely I want to do it. And actually it's not 2, but 1.96. All right? Well, and I'll show you how to find that value in just a minute. But you're right. That's exactly right, Brian. That's what we're trying to do, is come up with an interval. And the z value that you select is determined by how confident you want to be. So if you want to be 92% confident, you use a different z value than 95 and 99. Now, the more confident you want to be, the bigger that z is going to be, right? Because I'm going to have to go right, 99% confidence it has Z value is going to be bigger than 90%.
So depending on the confidence interval, it's 95% confidence interval. Z will be 2.
It's actually 1.96, but it's close to 2.
Okay. This is 2 standard deviations.
Right.
But this class will we use 2 or will we use 1?
We're going to actually use the number off the table.
Yeah.
The empirical rule is what you call a rule of thumb, right? So it's an estimate. 2 is approximately 95%. 1.96 is almost exactly 95%. All right, and I'm going to show you how to do that. All right. Okay, then once you add the probability to it by using the Z value, it becomes what we call a confidence interval. Okay, our goal is what? A narrow interval. Why is that? It's just like I was telling you earlier, right? What did I say? I said your final grade in the class is somewhere between 0 and 100. Thanks a bunch, right? That's a wide interval. We don't want it. We want it to be a little bit more precise, right? The problem is this. The more confident we want to be, do we want to have a lot of confidence in our interval, in our estimate? Yes. The more confident you want to be, the wider the interval gets. The less confident you'll settle for, the more narrow. So those are kind of competing, aren't they? We want a high level of confidence, but we want a narrow interval. The only thing that you can do to have both is what? Increase your sample size. The goals are in conflict, right? Okay, and many of the point estimates, which are the statistics, are normally distributed. All right, general format of the confidence interval is our best guess, which is what? Listen up, you guys. What's our best guess? If we're estimating the population mean, our best guess is the sample mean. That's our point estimate, right? So if we're estimating the population proportion, what's our best guess? The sample proportion, right? That's the corresponding statistic. Plus or minus, we use the term the number of steps because we're going to talk about a Z and a T. Okay? That means the Z is the number of standard deviations, right? And then it's times the step size, and the step size is the standard error or the standard deviation of our point estimate. So it's going to be a certain number of standard deviations. Okay? Our best guess is the point estimate. The number of steps is the function of the level of confidence. Comes through the Z or the T table. The step size is the standard error of the point estimate. All right? And honestly, this is incredibly easy. The theory behind it you may not understand. Coming up with a confidence interval is very easy. Okay, can you estimate it? Yes. Do you have to have a great understanding of the statistics? No. It's not necessary. It's not necessary to have some great understanding of the statistics. All right, now we're going to skip this. Let's see if I can do this without messing it up. I'm trying to close it so we can escape. All right. Gosh, I hope I don't screw this up. You guys hold your breath. Wow, do you want to add? I don't know. Okay, sorry. Okay, so why is that still in there? Okay, let's see. Why is that pen thing still there? You know what's wrong? Shoot, this is what he told me. No, it's back. Okay, there it is. I guess I still had it on pen. Okay, you guys.
Go to the left.
With the left where?
On the bottom. It's on the border right there. You're in the middle. Left.
Go here?
Left.
What do you mean, left where?
Up, go up 2 inches. Right there. Up. That's where you take it off. Put it back on the cursor, which is on the top.
There you go. All right, listen.
There it came up. Okay, thank you. Now I have no idea what I'm looking for. I've completely lost my train of thought. Okay, let's see. Oh, I'm looking for a table. Sorry. There it is. Okay, let's talk about the Z table first. So you have your own Z. I gave you a copy of it in the book, right? Or I gave you a copy that came from your book. Yeah, it doesn't get any bigger than that. Okay. All right, here's the cumulative probability table. Now, this table that you have in your book, this cumulative table, right? What we do is instead of, since we convert everything to a z, we only have to use one table for the probability of the normal distribution, right? And that probability table is found on the inside back cover of your book. It's the areas under the normal curve. There's more than one different way to present that table, but that I also gave it to you on a piece of paper. It's probably easier for you to look at. This particular table, and there are more than one, but this particular table shows you the area between the center of the distribution, which is what? 0, and a particular z value. Okay? If I can do this. Okay. See, and I didn't, this is the area, it says area under the normal curve from 0 to a particular value. Okay, from 0 to a particular value. Now, that's different, okay? That's different. Some tables are cumulative tables. Okay, in other words, a cumulative table for the normal would give you the area from negative infinity up to a value. So if you had a value here, obviously the center of that distribution is 0, but say the area, you might look up 0.78, and it would give you this total area from negative infinity up to that value. Okay, that's one example. This particular table doesn't do this. This one instead is going to give you the area between 0, which is the mean, and a particular z value. Okay? So this is the distribution of z, and this is 0. And so this, what we're going to do is say that we're going to use 1.0. So we want it, what we do when we go to 1 to find the value across the top, it'll give us the area between 0 and 1. All right, this is how you do it. To find the value, you're going to go like this. All right, we're going to do this. We're going to look here between, if I turn that off. All right, to find, and it calls it x, but we're looking for the z value. If you go down the left-hand side here, down to 1.0, then the second decimal place is going to be 1.00. You see that area right here, 0.34134, and I don't know what it is on yours, 0.3414, is that what it is on your table? 3413. 3413, this just happens to go to 5 decimal places. Okay, the one, I couldn't find one. You have to bring one in. You can't, I didn't scan it. I just found it online. All right, so what that says is the area between I'll draw it one more time. All right, so it's saying this. The area between 0 and 1 is what? 0.3413? 0.3413. So the area between 0 and negative 1 is what? It's symmetrical, 0.3413. So if you add those together, is that approximately 68% lie within one standard deviation of the mean? Right? One is the z value, right? We're looking at the z's. All right, so how do I find it? The total area under the curve, how do I find the area here and here? How would I find that?
Subtract it from 1.
I could subtract the total area, which is 0.6426, from 1, and then I'd split it in half to get each tail, right? Or how else could I do it? What did I tell you? 0.5 is to the right of the mean, right? So I can take 0.5 minus 0.3413, and that's the tail area, isn't it? Okay, so the areas here in the center of this table, these areas here are all areas, those are areas, and the values up here, right down here and across this way, this is to the first decimal place down the left-hand side, right? This is to the first decimal place of z. The second decimal place is across the top. Where they intersect is going to be the area, and the area that's given is the area from 0 to a particular z value. These are all positive. It doesn't matter whether it's positive or negative. It's going to give you the area between 0 and that value, whether it's positive or negative. Again, the z values to the first decimal place down the left-hand side, second decimal place across the top. All right, let's see if we can do this. All right, now, let's look up. Let's look 2. All right, so we go to 2 here. There's a 2, there's 2 right there, right? 2.00, what is that? 0.477, is it say 2 on yours?
Yeah.
All right. Again, I didn't draw that very well. You write 0.4772, is that right? Does everybody have a calculator? Okay, you need to bring it to class each time if it's not. All right, so if you add those together, what is it? 0.9544. So it's not exactly 95% within 2 standard deviations. It actually is 0.9544, so 95.44% between those two. Do you agree? All right, now, typically we are much more interested in the area in the tail than we are between 0 and some value. All right, so what we figured out, if we take 0.5 minus 0.4772, right, we get 0.0228. That area is here, and also it's over here. Do you agree? And the total area then would be 1. All right, so if I wanted to find an area, a z value that corresponds to a particular area in the tail, I want 95%. I want exactly 95%. So how do I do that? Well, think about it. Okay? I'm going to say, look, let's think about this. Okay, so I want 0.95 is in the center, right? 0.05, so really it's 0.025 in each tail, right? That's half of 0.05. Everybody agree? All right, so I'm looking for a z value that has 0.025 in the tail. Okay, so, but how do we know? How do we get this value? We know that the area in the table is what? Not 0.025, but what? It's going to be this area. Do you agree right here? That's the area that's in your table. Okay, so how do I get that value? We just did it a while ago to go backwards. So we take 0.5, which is the area right to the right of the mean or to the left of the mean, whichever way, minus the tail area that we want, 0.025. And what does it give us? 0.4750. And that's this area, 0.4750. Okay, now this time, instead of having a z value and finding the area, I'm going to back into it. So I'm going to look here in the body here for 0.4750. And they're in order. And here it is. You see it? All right, so we go all the way to the left to get to the first decimal place of the z, and it's 1.9. And then we go up to get to the second decimal place of z, and it's 1.96. So, if we have negative 1.96 has 0.025 to the left, and positive 1.96 has 0.025 to the right. All right, when we come up with our confidence interval, we're going to be looking for, that's how we're going to come up with these values based on tail areas for hypothesis testing. based on, and I'm going to show you how we're going to do it. We're going to back in. We're always going to use the tail area, and the only reason I say that is it's easier to learn it that way to begin with than to have to go back and learn it later. Okay, because you have to learn how to use the tail area anyway for hypothesis testing. All right, so you ready? We're going to see if we can find a particular area in the tail, and then we're going to know how to use the Z table, and we'll be great. All right. Let's see if we can find a Z value for 0.05 in the tail. All right. All right, 0.05, and it doesn't matter which side, we're talking about 0.05 in the tail. So what is this area here? The area between 0 and that area, that line right here. 0.5 minus 0.05 is what? 0.4500. 0.4500. We're going to, and again, it doesn't matter which side you're talking about because it's symmetrical, right? The tail area, 0.05. We're looking for a Z value that has 0.05 in the tail. All right, so we're looking at 0.4500. Oh, falls between two, doesn't it? We have this value and that value. 4495 and 4505. You see them? All right, so we go to the left. And it's 1.6, and you go up here, and it's 1.64, or here, the second decimal place, 1.65. We're always going to pick the value furthest from 0, okay? If we're talking about negative 1.65, it's the smallest value. Positive 1.65, it's the largest value. And we do that only to be conservative, okay? Don't worry about it. You're always going to pick the value further from the center. Further into the tail. There's a reason for it. It's conservative. And later when we start doing some estimation and hypothesis testing, then you'll be able to see why it's conservative, okay? All right, if it falls between two, the rule for any probability distribution, if you're looking for a critical value, is going to be take the value further from the center. Further into the tail to the right or into the tail to the left, depending on which value you're looking for, okay? For the Z and the T, since the center of the distribution is 0, you're always going to take the largest positive value, which corresponds to the smallest negative value. Everybody understand? All right. Think you can do this? You want to do one more, or are you ready to go on? You want to find one more Z value, or can you do it? And everybody talk at the same time. It's time to go, isn't it? Isn't it time to go? You're like, yes, it's time to go. All right. You have some values in there. Let me the handout that I gave you. This is what I'd like for you to do. On this homework, I'm not going to give you very much homework, but you can do it, whatever you think you can do. All right. You know what we're going to do is I'm going to show you a T real quick. Let me pull up the T value real quick. Okay, the T is so much easier. All right, in this case, whatever area we want in the tail is shown across the top. Degrees of freedom for this, we're always going to use the degrees of freedom are down the left. Ooh, I did not mean to do that. Sorry. Okay, degrees of freedom. Sorry. Okay, degrees of freedom are down the left-hand side. Here's 1 degree of freedom, 2, 3, and so forth. Your degrees of freedom for what we're going to be doing is, for this first one, is n minus 1. So if we have a sample size of 30, 30 minus 1 are 29 degrees of freedom. Okay? We calculated a while ago. 0.025 in the tail for the Z distribution, what was the value? 1.96. What is wrong? I can't get that to come down. I can look up there, right? All right, let's say, oh God, if I hit this thing. Okay, look, I hit it. I can't get it to move down. No. You have the T-table there. Let's just use something else. Let's say 22 degrees of freedom. We'll use 22 degrees of freedom here. Look across the top. We have 0.025 in the tail. We'll just look at one tail. There's 0.025 in the tail. You notice degrees of freedom 22 is 2.074. When you look up T values, you're going to look up the area first and then find the corresponding degrees of freedom by going down the left-hand side. If you notice, as degrees of freedom get larger, the T value gets smaller. We get smaller as we go down there. It's approaching, as you go down the thing, it approaches 1.96, which is the Z value for 0.025 in the tail. All right, look at your little handout, you guys. This estimation example, you see that? Suppose as owners of a competing restaurant, is that the one I gave you?
Yeah.
All right, what you're going to do is this. Minimum is you're going to read these problems and try to identify what they are. Look at the first problem. It says, suppose as owners of a competing restaurant, we would like to determine the typical amount spent. This is a sample of 36. What is 36?
Sample.
N. Sample size. N equals 36. Lowercase n. Okay, so we took a sample of 36 and we found the typical amount spent was 720. What is that? X bar. That's a sample mean. Typical amount is. So $7.20 is X bar. The standard deviation is S because it came from the sample of $1.50. All right? So what we were trying to do is we're going to construct a 90% confidence interval. I can't get anything to close. Okay. All right, so I'm going to write it on here. Okay, if we want to be 90% confident, then alpha is equal to 1 minus 0.9. What we're looking for whenever we do a confidence interval is we're going to come up with, we're again going to use X bar plus or minus, we're either going to use a T or a Z, and in this case we're going to use a T, times the standard error, which is sigma divided by the square root of n. If we don't know sigma, what do we have to use? S. S divided by the square root of your sample size. Okay? So, in this case, to come up with your T or your Z value, you have to know your level of significance. In this case, it's going to be 0.1, right? 1 minus 0.9. And we always use a T or a Z in a confidence interval that's half of that. So, we're going to use alpha divided by 2. It's going to be half of 0.1, which is 0.05. So it looks like this. We're going to have X bar plus or minus a T with the appropriate degrees of freedom because it calls for that, alpha divided by 2 in the tail, times S, because we don't know sigma, divided by the square root of n. All right. We're looking for a T with 0.05 in the tail, and how many degrees of freedom if my sample size is 36. 36, so we have 35. So you go down your table to 35 degrees of freedom on your T table. I hope you do. I gave you one.
The smallest degree of freedom we have is 7.
You look in your book. It's on the other side. It's inside that cover. Look at the other side. Turn it over. One more page. Okay. 0.0. We're looking for 0.05 in the tail, which actually they show you 90%, but 0.05 in the tail. We're looking for how many degrees of freedom? 35. 1.69. So that's your T value. So X bar we said was 720 plus or minus 1.69 times S, which was 150 divided by the square root of 36. This is a 90% confidence interval. 90%. We use CI for mu. Okay, what I just want you to do is go through Number 1, you look up a t-value for that. Number 2, we're going to use the proportion. I didn't give you this stuff, so let's skip that. Try number 1. Oh gosh, we have a bunch of these. Number 5, number 1, number 5, number 6, and number 7. What I would do is I would look for the confidence interval, I think it's chapter 9, and kind of review this for tomorrow. Confidence intervals are chapter 9 in your book. The proportions, and you might try those, but I didn't give you the formula for using the proportions. And I'm not going to mess with it now because I think you can do this. What I'd like for you to do is read each of these problems, determine if it's going to be a proportion or a mean, and how can you tell if it's a proportion? You have qualitative data, right? All you can do is count how many you have. In other words, number 2 is a proportion because it says you took a sample of 400, 298 are full-time. All you can do is say how many and calculate a proportion there. So you want to determine that. See how much of the stuff you can write down. On the ones that I told you, see if you can come up with a confidence interval. All right? You guys have a great time. Go to lunch. I will see you on Thursday.
So that answer basically would be we are 90% confident that the average price of the new restaurant would be between $6.78 and $7.62, which would be higher than our average price.
That's absolutely right. You're going to come up with the interval. We are 90% confident the true mean amount, whatever it was, falls in this interval.
Okay.
Good job.
Is that your?
The only thing I do, now see what I have a problem with is this. Once I get here, I can't move that. Even when I do this, I can't. Maybe I'll be able to now. Look at this. All you have to do is stand next to it. I could not do that. It didn't matter what it is. Yeah, and then I did that, but I could, for whatever reason, it wouldn't move. But it's probably just because you weren't standing next to it.
No, my bad. What was it? I don't want the doors probably
The carbon chair for eco.
No, that was wait.
All right, so just go ahead and hit stop.